Beyond the boundaries of our understanding, past the veil of reality as we know it, lies a vast expanse of the unknown, mysterious, perplexing, and brimming with possibilities. What truly lies beyond the event horizon of a black hole? Are we alone in this immense universe, or are there civilizations out there far more advanced than we could ever imagine? Join us as we venture into the strange realms of bizarre objects, enigmatic planets, and galaxies that challenge the very fabric of space and time. We will dive into groundbreaking theories, ones that push the limits of science and confront the deepest mysteries of our cosmos. But let us start with the black hole, a cosmic beast, a voracious entity that devours everything in its path, pulling in matter and light alike. Nothing escapes its grasp, not even light itself. Yet, in the heart of this dark, gravity-saturated abyss, there exists an equally intriguing entity, the white hole. This theoretical marvel, born from the same equations that describe black holes, is a paradox of sorts. Unlike the black hole that draws everything into its inexorable grip, a white hole would expel all matter and energy with such force that nothing could penetrate its bounds. Imagine an object that does the opposite of what we've come to expect, one that might very well serve as the cosmic mirror to a black hole. Though still speculative, the idea of a white hole is tantalizing. If such an entity were ever discovered, it could completely alter our understanding of space, time, and gravity. The implications would be staggering. It would introduce a concrete example of time symmetry in the realm of general relativity, the framework that governs our understanding of gravity. Just as a black hole traces the irreversible flow of time in one direction, a white hole might offer a glimpse of time symmetry, as if to trace the path of a black hole in reverse. Such a discovery could shed new light on some of the most puzzling phenomena in the universe, such as the information paradox surrounding black holes. While black holes are theorized to trap information, possibly forever, white holes might be the key to releasing it, giving us potential insights into how information is preserved in the universe. The study of white holes could unlock groundbreaking revelations about the nature of singularities, those points of infinite density that exist at the core of black holes, and even the very origins of our cosmos. Some cosmologists speculate that the Big Bang, the very birth of our universe, may have been a type of white hole explosion, one that scattered matter uniformly across the cosmos, shaping the universe as we know it. This transformative idea could challenge everything we know about creation and entropy on the grandest scale imaginable. Now, imagine traveling through space itself, not along the traditional path we know, but through a wormhole, those mysterious Einstein-Rosen bridges that promise to link distant regions of space-time. These hypothetical passageways are solutions to the equations of general relativity, and they suggest the possibility of shortcuts through space that could defy the laws of conventional travel. Picture space as a flat sheet of paper and a wormhole as a tunnel punctured through it. This tunnel could provide a direct path between two distant points, eliminating the need for conventional travel. If ever discovered and stabilized, wormholes would be the key to an unimaginable adventure. Approaching a wormhole, you would see stars twisting and contorting in ways never before imagined. Light would warp as if caught in a gravitational tug-of-war, creating a breathtaking visual phenomenon. As you enter, the experience inside would be instantaneous, but disorienting, distorted by the extreme gravitational forces. Time itself might behave unpredictably. Imagine emerging on the other side, having aged differently than those who took a traditional journey through space. The very fabric of time and space would be bent to your will. But there's a catch. These wormholes, if they exist, are unstable. They would require something far beyond our current understanding of physics to keep them open: exotic matter with negative energy density. Such matter has yet to be discovered, and its existence remains a mystery. Yet if humanity could one day harness the power to stabilize and navigate wormholes, it would redefine our entire understanding of space, time, and causality. And then there's the enigma of Oumuamua. In 2017, this interstellar visitor made headlines as the first known object from beyond our solar system to enter our cosmic neighborhood. With its elongated, cigar-like shape, measuring over 400 meters in length but only 40 meters wide, it was unlike anything astronomers had seen before. Its mystery deepens with every passing year as questions swirl around its true nature. Could it be a cosmic message, a probe sent from a distant, advanced civilization? Or is it simply a strange, natural phenomenon, a relic of the cosmos? Whatever the truth may be, Oumuamua serves as a reminder of the vast unknown that still lies beyond our grasp. In exploring these mind-bending possibilities, the black holes, white holes, wormholes, and interstellar objects like Oumuamua, we are confronted with the unfathomable complexities of the universe. Each of these phenomena challenges our understanding, forces us to reconsider what we know about space, time, and reality itself. We stand at the edge of an ocean of unknowns, waiting for the next breakthrough that could forever change the course of human history. And the question remains, are we truly alone in the universe, or is there a greater cosmic story unfolding, one that we are just beginning to comprehend? The universe holds secrets beyond our wildest dreams. Let us continue to search, to question, and to explore, for each discovery brings us one step closer to understanding the vastness of existence itself. When Oumuamua raced through our solar system, it exhibited a striking and unprecedented behavior. As it ventured beyond the gravitational reach of our sun, it accelerated in ways that defied the predictions made by conventional gravitational theories. This unexpected acceleration baffled astronomers, spurring a wave of hypotheses regarding its nature, origin, and purpose. Initially thought to be a typical comet, Oumuamua quickly cast aside this classification when it failed to display the iconic tail and gas emissions commonly associated with comets. Instead, it moved with the grace and unpredictability of an object, unlike anything we had observed before. Some scientists suggested that Oumuamua might be a fragment of a much larger object, perhaps an asteroid or planetesimal, that had been torn apart by the powerful gravitational forces within its home star system. Others, however, saw its strange acceleration as evidence of a more exotic and perplexing origin. This led to the birth of one of the most controversial theories about its nature. Could Oumuamua be an artificial object? The suggestion, put forth by physicist Avi Loeb, is that it might be a light sail, a thin, flat structure designed to harness sunlight for propulsion, launched by an advanced extraterrestrial civilization. Though this theory remains speculative and is unsupported by direct evidence, it highlights the enigmatic qualities of Oumuamua and underscores the limitations of our current understanding of cosmic phenomena. Despite the lack of definitive proof to confirm its origins, one thing is clear. Oumuamua has captivated the scientific community and reignited global curiosity about the vast, unexplored realms of our universe. As it passed through our solar system, its fleeting presence reminded us of the mysteries that remain beyond our reach. Whether it was a natural object or something far more extraordinary, Oumuamua's journey was a pivotal moment in the history of astronomical exploration. Yet, the universe has more enigmas to offer. Fast radio bursts, FRBs, are among the most perplexing and awe-inspiring phenomena ever discovered in the field of astrophysics. These brief but intense bursts of radio waves were first detected in 2007, lasting only milliseconds, yet releasing an amount of energy that could match the output of our sun over an entire day, or even a year, depending on the FRB. What makes these bursts even more puzzling is the fact that they originate from distant galaxies, suggesting that the energy behind them must be immense to travel such vast distances across the cosmos. The origin and cause of FRBs remain one of the greatest unsolved mysteries in modern science. One theory posits that these bursts are the result of cataclysmic events, such as the collision of neutron stars or the collapse of massive stars into black holes. Such catastrophic events could explain the tremendous energy released in each burst, but typically they would be one-time occurrences, not recurring phenomena. However, the discovery of repeating FRBs, such as the enigmatic FRB 112111002, has challenged this notion. The repetitive nature of these bursts has led some to propose that they could be linked to highly magnetized neutron stars, known as Magnetars, which release bursts of energy at regular intervals. Yet the most speculative and perhaps the most intriguing hypothesis is that FRBs might be artificial in origin. Could these bursts be signals sent out by extraterrestrial civilizations? Some have suggested that advanced alien technology might harness energy beams for propulsion or communication, producing these bursts as byproducts of their operations. Though this remains a minority view within the scientific community, it speaks to the wide range of ideas and theories that arise from our limited understanding of the universe. Regardless of their true origin, fast radio bursts challenge everything we think we know about the universe's energetic processes. They force us to confront the possibility that the cosmos may be far more complex and far more active than we could have ever imagined. Each new detection of an FRB adds another piece to the cosmic puzzle, one that beckons for further exploration, deeper study, and a relentless search for answers. Perhaps, in the near future, scientists will unravel the mysteries behind these bursts and discover profound truths about the nature of the universe itself. Until then, we are left with a sense of wonder and anticipation, waiting for the next breakthrough that will take us one step closer to unlocking the secrets of the cosmos. Rogue planets, those enigmatic wanderers of the cosmos, drift through the cold voids of space, severed from the gravitational embrace of any star. These celestial outcasts, though largely hidden from our view, are believed to be as abundant as the stars themselves. Yet, despite their elusive nature, they continue to spark the curiosity of scientists and astronomers. As they journey through the dark expanses of the universe, their surfaces remain locked in perpetual night, where temperatures plummet far below what we could ever experience on Earth. But what secrets do these solitary planets harbor beneath their frozen exteriors? Though shrouded in darkness, rogue planets may not be as barren as we imagine. Geothermal activity within their cores could potentially give rise to subsurface oceans, much like those theorized to exist on moons such as Europa and Enceladus in our very own solar system. These hidden seas, heated by the planet's internal heat, could be a haven for microbial life. If life can thrive in the extreme environments of hydrothermal vents deep beneath Earth's oceans, could it also find a way to survive in these distant, dark worlds? The absence of sunlight does not eliminate the possibility of life. Instead, it challenges our understanding of where life can take hold. These deep, dark oceans could have chemical energy sources that would sustain life forms without the need for sunlight. Beyond the potential for life, rogue planets also serve as cosmic time capsules. Ejected violently from their home systems, these planets may carry with them clues about their origins, the conditions of the stellar systems they once belonged to, and the planetary processes that led to their current state. By studying rogue planets, we can gain invaluable insights into planetary formation, migration, and the dramatic interactions that result in the solitary journeys of these worlds. In addition, these wandering planets offer a unique opportunity to study planetary atmospheres in isolation, free from the overwhelming influence of stellar radiation. As our technology advances, these drifting worlds, once invisible to us, will come into sharper focus, providing insights that could forever change our understanding of the cosmos and our place within it. Neutron stars, on the other hand, are a class of celestial objects that stretch the boundaries of our understanding of matter and physics to their limits. Born from the violent deaths of massive stars that have exhausted their nuclear fuel, neutron stars are dense beyond imagination. A neutron star's mass can exceed that of our sun, all contained within a sphere barely 20 kilometers across. To put it into perspective, a single teaspoon of neutron star material would weigh approximately 1 billion tons on Earth, revealing densities so extreme they defy our common experience of matter. What gives these stars their extraordinary properties is the compression of atomic nuclei within them. In a neutron star, protons and electrons are crushed together, merging to form neutrons, which leads to the creation of a unique state of matter known as neutron degenerate matter. Yet, even this might only be the beginning. Some theories propose the presence of even more exotic states of matter within neutron stars, such as quark-gluon plasma, where neutrons break down into their constituent quarks. In some cases, strange matter, made of strange quarks, may even exist in the cores of these stars. These extreme conditions make neutron stars perfect natural laboratories for testing our theories of quantum mechanics and nuclear physics, subjects that are impossible to replicate on Earth. Neutron stars also give rise to some of the most mind-boggling phenomena in the universe, such as pulsars. These rapidly rotating neutron stars emit beams of radiation that sweep across space like lighthouse beams, appearing as regular pulses when observed from Earth. The incredible rotational speeds of neutron stars, sometimes hundreds of times per second, coupled with their magnetic fields, which are trillions of times stronger than Earth's, make them sources of high-energy processes that challenge our understanding of electromagnetism and general relativity. The gravitational field around a neutron star is so intense that it warps the very fabric of space-time, offering a real-world test of Einstein's theories and providing crucial insights into the curvature of space. Studying these celestial titans not only enhances our understanding of how the fundamental forces of nature interact under extreme conditions, but also provides essential tests for the theories that may one day unite all the known forces of the universe. Neutron stars, like rogue planets, offer an extraordinary opportunity to explore the very edges of our knowledge, pushing the boundaries of what we understand about matter, energy, and the universe itself. Strange matter, a mysterious and exotic form of matter, is composed of strange quarks in combination with the more familiar up and down quarks that make up protons and neutrons. Under typical conditions, strange quarks do not readily combine with other quarks. However, in extreme environments like those found within the cores of neutron stars, strange quarks might form stable clusters. This theoretical state of matter is incredibly dense and stable, unlike anything we can replicate in earthly laboratories. By studying this, scientists might unlock new insights into the behavior of subatomic particles at energy levels that are impossible to reach on Earth. The concept of strange matter arises from the extreme conditions within the dense cores of neutron stars. Neutron degenerate matter, already tightly packed from the collapse of a star, could potentially undergo a transformation into strange matter. This transformation would result in a star denser than a neutron star, known as a strange star or quark star. These hypothetical stars would have an extraordinarily high binding energy, allowing them to absorb ordinary atomic nuclei and assimilate them into strange matter. Upon contact, they could form stable strange matter states. The discovery of such stars would revolutionize our understanding of stellar evolution and the life cycles of stars. Imagine stars that could assimilate other matter, creating a chain reaction of transformation. If strange matter exists in the universe, its discovery would significantly impact our understanding of physics. It would provide empirical evidence supporting theoretical models that predict the existence of strange matter, validating ideas about quark deconfinement, a process in which quarks, typically confined within protons and neutrons, are freed under extreme conditions. This would also open a unique window into the behavior of the strong nuclear force, the powerful interaction that binds quarks together. A breakthrough in understanding strange matter could even have cosmological implications, such as influencing the birth of neutron stars or altering our theories on the rates of supernovae. This exploration of extreme states of matter would challenge our fundamental concepts of matter's stability, paving the way for future research into the nature of exotic matter in the universe. Beyond strange matter, another deep mystery in cosmology is dark matter. Dark matter, which constitutes roughly 85% of the universe's mass, is completely invisible. It does not emit, absorb, or reflect light, making it undetectable by conventional means such as electromagnetic observations used to study stars and galaxies. Despite this, scientists have inferred its existence through its gravitational effects. For example, the rotational speeds of galaxies and the bending of light around massive objects, a phenomenon called gravitational lensing, cannot be explained by visible matter alone. This strange behavior suggests the presence of a massive, unseen force at work in the universe. To study dark matter, scientists have devised clever techniques to detect it. One approach is direct detection, where experiments are set up to observe potential interactions between dark matter particles and normal matter. These experiments are usually conducted deep underground, away from cosmic rays and other background interference. Special detectors, often filled with supercooled liquids or solid-state targets, are used to monitor for rare collisions with dark matter particles. These interactions might produce tiny flashes of light or vibrations, which can be detected by sensitive equipment. The Large Underground Xenon Experiment, LX, and its successors are among the projects trying to observe such interactions. Another method is indirect detection, which seeks out the byproducts of dark matter annihilations or decays. As dark matter particles collide and annihilate each other, they may release gamma rays, neutrinos, or positrons, particles that astrophysical observatories can detect. Both ground-based and space-based observatories search for these byproducts. Instruments like the Fermi Gamma Ray Space Telescope and the Alpha Magnetic Spectrometer, located on the International Space Station, are on the front lines of this search. Together, these efforts may one day provide the breakthrough needed to finally understand the elusive nature of dark matter. In the quest to uncover the fundamental forces of the universe, cutting-edge research has led scientists to explore the farthest reaches of space. Particle accelerators like the Large Hadron Collider, LHC, are at the forefront of this exploration. By recreating conditions akin to those moments after the Big Bang, these massive machines have the potential to produce dark matter particles, particles that could hold the key to some of the most profound mysteries of the cosmos. However, experimental approaches are only part of the puzzle. Theoretical physics is also advancing through simulations that predict the gravitational effects of dark matter on the vast structures of the universe. Advanced computer models and algorithms play a crucial role in predicting how galaxies form and cluster under the influence of this invisible force, guiding observational strategies and shaping our understanding of the universe's hidden architecture. As technology advances and our theoretical frameworks evolve, the enigmatic nature of dark matter will come into sharper focus. These efforts are more than just an academic pursuit. They could lead to breakthroughs that revolutionize our understanding of the universe's fundamental composition and the forces that govern it. With each new discovery, scientists inch closer to unlocking the secrets of a dark and invisible substance that makes up a significant portion of the universe, yet remains elusive to detection. Amidst the search for dark matter, another awe-inspiring cosmic phenomenon has captured the attention of astrophysicists: magnetars. These stellar remnants, a particularly extreme form of neutron stars, are distinguished by their incredibly powerful magnetic fields. Magnetars possess magnetic fields up to 1,000 times stronger than typical neutron stars, fields so powerful that they can reach up to 1,000,000,000 times stronger than Earth's magnetic field. These immense fields are capable of compressing atoms and even distorting the very fabric of space itself, creating environments that challenge our understanding of physics. Magnetars offer an unprecedented opportunity to study matter under the most extreme conditions imaginable. One of the most intriguing mysteries they may help unravel involves the behavior of matter within ultra-intense magnetic fields. In these environments, atomic structures could be drastically altered, with electrons being forced into tight, spiraling orbits near the nucleus. This could give rise to bizarre states of matter that differ vastly from those observed under normal conditions on Earth. Such observations could provide profound insights into quantum electrodynamics, QED, the quantum field theory that describes the interaction between light and matter under extreme conditions. These environments, which cannot be replicated on Earth, may hold the answers to some of the most complex questions in physics. Moreover, magnetars are not just cosmic oddities. They are also sources of some of the most energetic phenomena observed in the universe. For instance, soft gamma-ray repeaters, SGRs, and anomalous X-ray pulsars, AXPs, are both associated with magnetars. These high-energy emissions are the result of starquakes, crustal fractures that occur due to intense magnetic stress. The subsequent release of magnetic energy during these events provides a rare glimpse into the dynamics of ultra-dense matter and the complex interactions between magnetic fields and crustal stresses. Understanding these mechanisms could unlock new perspectives on the behavior of matter under extreme pressures. Additionally, the intense conditions within magnetars might facilitate the formation of exotic particles or even entirely new states of matter. The formation of quark matter, for example, could occur under such extreme conditions, potentially even giving rise to more exotic forms of matter, such as strange matter. Detecting radiation or unique signals emanating from these states would provide crucial evidence to support theories about the fundamental nature of matter itself. The study of these phenomena could thus open new frontiers in our understanding of the universe at the most fundamental level. Beyond the internal dynamics of magnetars, their intense magnetic fields also challenge and expand our understanding of magnetohydrodynamics, MHD, the study of the magnetic properties and behavior of electrically conducting fluids, such as plasmas. Magnetars push the boundaries of what we know about MHD, offering a natural laboratory where these theories can be tested in ways that terrestrial experiments never could. Yet, magnetars are not the only cosmic wonders that spark curiosity in the scientific community. There are also the velocity stars, stellar speedsters that defy conventional expectations. These stars exceed the typical velocities of stars in the Milky Way, and some even achieve speeds fast enough to escape the gravitational pull of the galaxy entirely. How do they reach such extraordinary velocities? One compelling theory suggests that these stars are accelerated by the supermassive black hole at the center of our galaxy. Through highly energetic gravitational interactions, velocity stars can be flung into space at speeds that defy comprehension, offering another unique window into the forces that shape the cosmos. As our understanding of these cosmic phenomena deepens, the mysteries of the universe continue to unfold. Whether it's unraveling the secrets of dark matter, exploring the exotic states of matter within magnetars, or studying the high-speed trajectories of velocity stars, each discovery pushes the boundaries of our knowledge and brings us closer to understanding the fundamental forces that govern everything from the smallest particles to the largest galaxies. Sagittarius A, the supermassive black hole at the heart of the Milky Way, is an enigmatic and powerful force. When a binary star system ventures too close to its gravitational grasp, intense tidal forces are unleashed, often with dramatic consequences. In these extreme conditions, one star is irresistibly pulled into the black hole's singularity, while its companion is violently flung into space at speeds that can surpass millions of kilometers per hour. This cosmic ballet, triggered by the immense gravitational power of Sagittarius A, illustrates the destructive and awe-inspiring forces at play in the depths of our galaxy. But this is not the only scenario where hypervelocity stars are born. In densely packed stellar environments, such as globular clusters or the remnants of supernova explosions, close encounters between stars can lead to significant gravitational slingshots. These slingshots can accelerate stars to velocities so high they escape the gravitational pull of the cluster entirely. The result? A hypervelocity star, ejected at speeds that defy the typical behavior of stars. Even more remarkable is the role of supernova explosions. When one star in a binary system explodes, the surviving companion is often sent hurtling into space at astonishing speeds. This asymmetric explosion propels the companion away, creating a hypervelocity star in the process. These stars, once part of a system, are now rogue wanderers, tracing a path across the vastness of our galaxy. The study of these hypervelocity stars is much more than a captivating cosmic tale. It holds profound implications for understanding the structure and dynamics of our galaxy. By tracing the paths of these stars, astronomers can glean insights into the distribution of dark matter, that elusive substance that constitutes much of the mass in the Milky Way. Hypervelocity stars act as cosmic probes, mapping out the gravitational potential of the galaxy and offering the first hints at the shape and extent of the dark matter halo that surrounds our galaxy. Their paths serve as a guide, illuminating the otherwise invisible framework of dark matter that holds our galaxy together. Moreover, the origins of hypervelocity stars provide crucial information about the forces at work near the center of the Milky Way, where the gravitational field of Sagittarius A star exerts a profound influence on its surroundings. These stars, born from extreme interactions, offer a rare window into the processes occurring in one of the most energetic and enigmatic regions of the galaxy. Their study can unlock the secrets of star formation and dynamics in the high-gravity environment of the galactic center. Hypervelocity stars are also invaluable in tracing the history of stellar populations. By analyzing the composition, age, and chemical makeup of these stars, astronomers can uncover the conditions that led to their formation. These cosmic travelers offer a glimpse into the conditions of specific regions in the galaxy, shedding light on the star formation events that took place long before their ejection. The study of their dynamics and composition helps us understand the birth of stars in environments shaped by forces far beyond our current technological reach. Hypervelocity stars in their rogue existence carry with them the stories of the violent forces that shaped them. They are messengers from the very heart of the galaxy, revealing details about the unseen forces that govern the universe. As they travel through space, they leave behind a trail of clues about the gravitational dynamics, astrophysical processes, and invisible structures that shape the galaxy. Shifting our focus from the stars themselves to the broader cosmic landscape, we arrive at one of the most fascinating concepts in modern physics, the idea of alternate dimensions and parallel universes. These ideas have captured the imagination of both scientists and the general public, offering tantalizing possibilities beyond the limits of our understanding. In theoretical physics, these ideas are often explored within the frameworks of string theory, M theory, and the multiverse hypothesis. String theory proposes that the fundamental particles we observe are not point-like objects, but tiny vibrating strings. These strings exist in a higher dimensional space, potentially encompassing up to 10 or 11 dimensions. While we experience the world in 3 spatial dimensions and 1 time dimension, string theory suggests that these additional dimensions could be curled up or compactified in such a way that they are imperceptible to us. Parallel universes, as suggested by the multiverse hypothesis, present a mind-bending proposition. One version of the multiverse, known as the many worlds interpretation of quantum mechanics, suggests that every quantum decision, every choice made at the quantum level, creates a new branching universe. These universes would exist in parallel, each with its own version of reality. Meanwhile, another variation, the bubble universe theory, posits that different regions of space could undergo inflation at different rates, creating isolated bubbles that eventually evolve into separate universes. These universes might have entirely different physical constants, making them vastly different from our own. Detecting alternate dimensions or parallel universes is an enormous challenge. Yet scientists are pursuing a range of ingenious methods to uncover evidence. High-energy particle collisions, such as those conducted at the Large Hadron Collider, LHC, may provide the clues needed to unlock these mysteries. By simulating the high-energy conditions of the early universe, the LHC could provide hints about the existence of extra dimensions or other universes, offering a glimpse into a reality far beyond our current understanding. In the end, the search for hypervelocity stars and the exploration of alternate dimensions both share a common goal: expanding the boundaries of human knowledge. They push us to think beyond the known, to explore the unseen forces and dimensions that shape our universe. Whether through the stars that escape the grip of black holes or through the quantum mechanics that govern the fabric of reality, humanity's quest for understanding continues, driven by curiosity and the desire to uncover the hidden truths of the cosmos. If extra dimensions exist, they might reveal themselves in subtle yet profound ways, challenging our understanding of the very fabric of reality. One of the most intriguing possibilities is that these dimensions could manifest through missing energy and momentum in particle reactions. In such events, particles might be leaking into these unseen realms, a phenomenon that could remain undetected in conventional particle physics experiments, but could explain certain anomalies we observe. Moreover, the discovery of extra dimensions may not be confined to the world of particle physics alone. Advances in gravitational wave observatories, which are now capable of detecting the faintest ripples in space-time, could uncover the presence of these hidden realms. If extra dimensions exist, they might influence the gravitational waves passing through our universe, revealing subtle distortions that point to their existence. This cutting-edge technology has already given us glimpses into the deepest aspects of space, and it could one day provide the key to understanding dimensions beyond our perception. Cosmological observations, too, offer tantalizing potential insights. For example, the cosmic microwave background radiation, the faint afterglow of the Big Bang, could carry imprints of interactions with higher dimensions or parallel universes. Variations or irregularities in this radiation might be the result of such interactions, offering us a cosmic fingerprint of extra-dimensional forces at play. This hypothesis aligns with ideas in modern physics, suggesting that the early universe might have been influenced by events beyond our current understanding. But the exploration doesn't stop there. Dark matter and dark energy, the mysterious substances that make up most of the universe's mass energy content, could hold clues to the existence of extra dimensions. Current theories speculate that these enigmatic forces might be influenced by higher dimensional spaces, or even be a result of interactions with parallel universes. While these concepts are still on the fringes of scientific thought, they inspire an ever-growing body of research and experimentation, refining our understanding of the cosmos in ways previously unimaginable. The possibility that extra dimensions or parallel universes could exist is, at its core, revolutionary. If proven, it would forever change how we perceive our reality. It would expand the horizon of what the universe is and what it could be. The idea that our universe is just one of many, potentially infinite universes existing in parallel to one another is both thrilling and humbling. As technology and theoretical models advance, the quest to uncover these hidden realms continues to ignite curiosity, pushing the boundaries of human knowledge. One of the most compelling ideas in this quest is the theory of the multiverse. While it remains speculative, the multiverse suggests that our universe might be just one of an immense, possibly infinite, number of universes, each with its own set of physical laws and properties. This concept isn't just rooted in wild speculation, but is supported by frameworks in modern physics, including the theory of cosmic inflation. Cosmic inflation posits that the universe underwent a rapid expansion just moments after the Big Bang, a process that could have generated multiple separate bubble universes. Each of these universes would be distinct, with different physical properties and potentially even different laws of nature. Quantum mechanics, too, lends support to the multiverse theory. The many worlds interpretation, which is one of the most debated interpretations of quantum mechanics, suggests that every quantum event spawns a new parallel universe in which all possible outcomes of that event occur. This interpretation provides an elegant solution to the seemingly random nature of quantum phenomena, offering a view of reality where every potential outcome exists in its own parallel universe. Although the many worlds interpretation is not universally accepted, it adds a layer of intrigue to the multiverse concept. Observational evidence, while still indirect, also points to the possibility of a multiverse. Anomalies in the cosmic microwave background radiation could be signatures of interactions between our universe and others. Some researchers have even proposed that unusual cold spots in the CMB could be remnants of past collisions with other universes, providing tantalizing evidence of the multiverse's existence. These theoretical and observational clues all come together to form a compelling narrative, one where the boundaries of our universe are not as fixed as they once seemed. As we delve deeper into the mysteries of the cosmos, the lines between what is possible and impossible blur, opening up new avenues of exploration that could forever alter our understanding of reality. However, these interpretations of the multiverse theory remain highly contentious, stirring intense debate within the scientific community. They demand more rigorous testing and a wealth of new data before they can be definitively substantiated. The implications of the multiverse theory, should it hold any truth, are nothing short of profound. If our universe is but one among an infinite collection of universes, it shatters the conventional notion that we exist in a singular, unique reality. Instead, it opens the door to a mind-boggling possibility: countless versions of events, histories, and even entire existences unfolding across multiple realities. Such a theory fundamentally challenges our understanding of causality and the very essence of existence. If the multiverse is indeed real, it could reshape our perception of everything from the formation of stars to the emergence of life itself. For instance, the concept that our universe appears fine-tuned for life could be explained by the multiverse's potential to host a vast array of universes, each with its own set of conditions. In such a scenario, it would be no surprise that at least one of these universes, ours, has the precise conditions necessary for life to arise. The idea suggests that our universe is not a miraculous anomaly, but simply one outcome in a cosmic game of probabilities. Furthermore, the acceptance of the multiverse theory could spark revolutionary breakthroughs across multiple fields of physics. Imagine new revelations about the fundamental forces and particles that govern our universe. Even more tantalizing is the potential for the theory to bridge the existing gap between quantum mechanics and general relativity, two pillars of modern physics that have stubbornly refused to coexist peacefully. For years, these frameworks have been incompatible, unable to explain certain phenomena in a unified way. A multiverse could provide the key to resolving this age-old puzzle. Yet, despite the vast potential of this idea, the multiverse theory remains speculative. While the technology and theoretical models continue to evolve, we may one day find more tangible evidence to support its claims. Until then, it remains an intellectually stimulating, provocative concept, an idea that invites us to stretch the boundaries of our understanding and ponder the very fabric of reality itself. In the world of theoretical physics, the holographic principle represents another radical and compelling idea. This theory suggests that the entire universe we experience could, in fact, be a two-dimensional information structure encoded on the cosmological horizon. Such a proposition challenges the fundamental assumption that we live in a three-dimensional space. Born from deep investigations into the behavior of black holes, the holographic principle was developed to address paradoxes concerning information and entropy in these dense cosmic objects. The principle gained traction thanks to the work of brilliant physicists like Gerard Hooft and Leonard Susskind. Their insights were informed by Stephen Hawking's groundbreaking discovery that black holes emit radiation and eventually lose mass, a process that led to what is known as the information paradox. According to traditional physics, any information about the state of matter falling into a black hole would be lost as the black hole evaporates, violating quantum mechanics' sacred principle that information must always be conserved. The holographic principle proposes a solution to this paradox by suggesting that all the information about a black hole's three-dimensional interior can, in fact, be encoded on its two-dimensional event horizon. Expanding this idea to the entire universe, the holographic principle posits that the physics we observe in our three-dimensional universe is actually encoded on a distant two-dimensional surface. This would mean that our perception of depth, volume, and space itself is an illusion, like a hologram where a three-dimensional image is reconstructed from two-dimensional data. This view invites a radically different perspective. The fundamental essence of reality could, in fact, be information itself, encoded on a lower dimensional boundary rather than existing as tangible matter. Embracing the holographic principle requires a complete reimagining of space-time, suggesting that the complexity of the universe we experience is an emergent phenomenon arising from this more fundamental informational substrate. It carries the tantalizing possibility of unifying the seemingly incompatible theories of quantum mechanics and general relativity, offering a new lens through which to explore the very fabric of space-time and the nature of gravitational interactions. While testing this principle experimentally remains an enormous challenge, promising areas of research are underway, including the study of the ADS-CFT correspondence, a concrete manifestation of the holographic principle developed by physicist Juan Maldacena. This framework has already provided powerful insights into quantum gravity, black hole thermodynamics, and quantum field theories, pushing the boundaries of our knowledge of the universe. As we delve deeper into these profound concepts, one thing becomes clear. We are on the verge of understanding the universe in ways that could redefine not only our place in it, but the very nature of existence itself. The journey ahead is one of intellectual exploration, where theory meets imagination and the boundaries of reality are stretched to their breaking point. Ultimately, if the holographic principle holds true, it could lead to one of the most profound paradigm shifts in our understanding of the universe. It invites us to reconsider not only the very nature of dimensions, but also the fundamental elements that constitute reality itself. This theory suggests that our universe, in some unimaginable way, might be encoded onto a distant, lower dimensional surface, much like a hologram projects a 3D image from a 2D surface. As radical as this may sound, such a revelation could potentially offer a pathway to reconcile some of the deepest, most perplexing mysteries in theoretical physics. This brings us to another captivating idea, the simulation hypothesis. The proposition that our universe could be a giant simulation has profound implications for everything we know: reality, ethics, existence. Popularized by thinkers such as philosopher Nick Bostrom, the simulation hypothesis suggests that what we perceive as reality, with all its complexity, might actually be the product of a vast, highly advanced computational process. Imagine a reality governed not by organic laws, but by the code of an advanced civilization's hardware, a simulation so intricate that it feels indistinguishable from true reality. If we accept this hypothesis, we are faced with the disorienting idea that the world around us, every particle, force, and constant that we study, may merely be part of a sophisticated program designed to mimic the richness of an authentic universe. Much like the pixels on a screen forming images that hold no inherent substance, our physical reality might not possess true substance either. The universe, as we understand it, could simply be a grand illusion crafted by code. This insight shatters the traditional notion of objective reality. Philosophically, it challenges us to think of the universe not as a collection of physical facts, but as an informational construct. This viewpoint pushes us to consider reality as something fundamentally digital or computational. The implications for ethics are equally profound. If we live in a simulation, do our actions and experiences lose their significance? Some argue that whether simulated or not, our subjective experiences are real to us, and thus the importance of our ethical actions remains unchanged. However, others raise an intriguing question. If we are in a simulation, do the simulators bear any moral responsibility toward us? Do they have obligations to ensure our well-being, or are we simply an experiment in their digital landscape? The hypothesis also forces us to reconsider questions of determinism and free will. If the universe is indeed a simulation, it could be governed by predetermined codes and algorithms, essentially a version of hard determinism. However, this doesn't rule out the possibility that the creators of our simulation might have embedded random, emergent phenomena, allowing for a semblance of free will within the otherwise deterministic structure. Could this be the key to understanding free will within a simulated universe? But how could we detect whether our universe is a simulation? Some scientists believe that by looking for anomalies in the fabric of space-time, such as pixelation at the smallest scales or irregularities in the cosmic microwave background, we might find clues that suggest a hidden code. High-energy processes at the quantum level could reveal inconsistencies if they deviate from what we expect in a base reality. These theoretical signatures may represent the cracks in the facade of a digital world. Yet we are still far from any definitive test. Now imagine embracing the simulation hypothesis not as a hypothetical experiment, but as an existential framework. What does it mean for us as conscious beings? If we are part of a simulation, are we merely an experiment, or are we the creators of future simulations ourselves? Such questions propel us beyond the borders of science into the realms of philosophy, metaphysics, and even ethics. They prompt us to contemplate our origin, purpose, and destiny within a potentially infinite cascade of simulated realities. Whether or not the simulation hypothesis proves true, it serves as a profound thought experiment that challenges the very foundations of knowledge, reality, and existence. It urges us to look deeper into the nature of consciousness and the cosmos, reconsidering what it truly means to exist in a possibly simulated universe. And then there is the strange and mysterious phenomenon of quantum entanglement. Imagine two particles that are so intricately intertwined that the state of one instantaneously determines the state of the other, no matter how far apart they are, an effect so perplexing that it confounded even Albert Einstein, who called it spooky action at a distance. In experiments, we've seen this strange phenomenon manifest time and again. When the properties of one particle change, its entangled partner responds instantly, even if they are separated by vast distances, defying our conventional understanding of physics. This phenomenon suggests a deep, hidden connection between particles, one that doesn't adhere to the classical laws of physics, where information cannot travel faster than light. And from here, we plunge even further into speculation. What if this entanglement, This connection extends beyond individual particles. What if our entire universe, or even multiple universes, are connected in a similar, mysterious way? Could quantum entanglement hint at a deeper, interconnected structure of reality itself, one that transcends the limitations of space, time, and even our own understanding of physics? What does this reveal about the universe, or universes, that we exist in? The mysteries of quantum mechanics invite us to venture deeper into the speculative, ever-expanding world of interconnected realities, where the boundaries between what we know and what we can only imagine blur in ways we are just beginning to explore. The concept of a multiverse is mind-boggling, and if true, it could completely alter our understanding of reality itself. The idea that our universe is just one among many could be the key to unlocking some of the deepest mysteries of existence. Quantum entanglement, a phenomenon where particles become linked across vast distances, might be the thread connecting these parallel realms. Imagine that particles entangled across universes could carry out actions in one universe that ripple across the others. Such a scenario would present a fascinating challenge to our current notions of space, time, and causality. While still speculative, some physicists believe that this entanglement could serve as indirect evidence of these parallel universes, providing the proof we've long been searching for. If we could observe these phenomena, we may be forced to reconsider the very fabric of reality itself, possibly unveiling a profound, interconnected architecture that binds the cosmos together. In the depths of our universe, there lies an enigma that has puzzled scientists for decades: the Great Attractor. This mysterious gravitational force, located around 150 million light-years away in the direction of the Centaurus constellation, is exerting an immense pull on our Milky Way galaxy, as well as thousands of other galaxies. The force is so powerful that it is dragging entire galactic clusters toward it, yet the Great Attractor itself remains frustratingly elusive. Despite its enormous influence, its exact nature remains shrouded in mystery, primarily due to its location behind the dense plane of our galaxy. This obscured region makes it nearly impossible to observe with traditional telescopes. So, what could be hiding in this cosmic void? Some scientists speculate that it could be a vast concentration of dark matter, a mysterious and invisible substance that constitutes about 27% of the universe's mass and energy. If true, this discovery could revolutionize our understanding of dark matter, one of the most perplexing phenomena in modern cosmology. Alternatively, the Great Attractor could be a supermassive galactic cluster, so dense and powerful that it outshines anything we've encountered so far. Unlocking the secrets of the Great Attractor could offer not only a glimpse into dark matter, but also the forces that shape the very structure of our universe. The notion of a boundary to the universe challenges everything we think we know about space and time. If such a boundary exists, it would have profound implications for our understanding of the cosmos. Traditional cosmology suggests that the universe is finite yet unbounded. Much like the surface of a sphere, no matter how far you travel in one direction, you'll eventually return to your starting point. This model, rooted in general relativity, describes a universe that curves back on itself without a discernible edge. But if the universe does indeed have a boundary, it forces us to rethink everything we've understood about the structure of space-time. What lies beyond this boundary? One possibility is that it could lead to the multiverse, a vast collection of parallel universes, each with its own set of physical laws, constants, and dimensions. These universes would be incomprehensible to us, governed by principles that might defy our basic understanding of physics. Alternatively, some physicists propose the existence of a higher dimensional space, known as hyperspace, that extends beyond our perceptible universe. This theoretical realm could exert influences on our universe, shaping its behavior in ways we cannot directly observe. While these ideas are still speculative, they encourage us to stretch the limits of our imagination and challenge our perceptions of reality. Cosmic inflation is another groundbreaking concept that reshapes our understanding of the early universe. Proposed in the early 1980s by physicist Alan Guth, cosmic inflation suggests that in the first fraction of a second after the Big Bang, the universe expanded at an unprecedented rate. In a mere trillionth of a trillionth of a trillionth of a second, the universe grew from subatomic scales to vast astronomical dimensions. This rapid expansion smoothed out irregularities in the cosmos, creating a homogeneous energy distribution that paved the way for the formation of galaxies, stars, and all the complex structures we see today. This theory helps resolve several long-standing puzzles in cosmology, including the horizon problem and the flatness problem, by explaining why the universe appears so uniform despite being so vast. It also offers a framework to understand the genesis of the universe, providing insight into its earliest moments. As we continue to probe the origins of the cosmos, cosmic inflation remains one of the most important concepts in modern physics, offering us a tantalizing glimpse into the very birth of everything we know. One major conundrum the theory of inflation resolves is the horizon problem. This issue arises from the observation that, despite the universe being 13.8 billion years old, it remains incredibly uniform in temperature and density, even in regions that are so far apart that they could never have been in causal contact with one another. How, then, did distant regions achieve this level of uniformity? Inflation provides an elegant answer by suggesting that these regions were once in close proximity before an incredibly rapid expansion stretched them far apart, leading to the uniformity we observe today. Moreover, inflation also addresses the flatness problem, explaining why our universe appears to be geometrically flat rather than curved. Without this exponential expansion in the very early universe, our cosmos would likely have been drastically curved, one way or another. By probing the precise parameters of inflation, cosmologists continue to delve deeper into understanding its implications. The cosmic microwave background radiation, which carries the faint afterglow of this tumultuous period, provides crucial data about this early epoch. Understanding cosmic inflation is akin to piecing together the very blueprint of our universe, bringing us ever closer to uncovering the dawn of time itself. As we turn our gaze towards the far future, one speculative but intriguing scenario looms large: the Big Rip. In this theory, the universe's accelerating expansion, driven by the mysterious and poorly understood force known as dark energy, could eventually grow so dominant that it tears apart every cosmic structure, from galaxies to atoms themselves. It starts subtly. Galaxies drift further apart at an ever-increasing pace. Over time, this expansion will surpass the gravitational bonds holding galaxies together, causing them to fragment. As the expansion accelerates further, star systems will be the next to suffer, with stars and planets gradually being pulled apart, overwhelmed by the cosmic force. The consequences of this expansion would continue to escalate until even the very atoms that make up matter could no longer maintain their cohesion. Electrons might be stripped from their nuclei, causing the breakdown of matter itself. In the final moments before the Big Rip, space and time could be stretched beyond their limits, fragmenting into nothingness. This harrowing scenario, while still theoretical, has propelled significant research into dark energy, and understanding it is critical in determining the ultimate fate of our universe. Will the cosmos end with a gentle fade in a cataclysmic collapse, or in this dramatic, universe-shattering Big Rip? Another fascinating and speculative theory that has emerged from cosmological research is the multiverse theory, which suggests the existence of multiple universes, each with its own unique set of physical laws. These universes, if they exist, could diverge in ways we can hardly imagine, shaped by variations in fundamental constants, dimensions, and natural laws. Imagine, for instance, a universe where the gravitational constant is much stronger or weaker than in our own. In a universe governed by stronger gravity, stars would burn out far more quickly, collapsing into black holes at a staggering pace, preventing the formation of stable planetary systems. In such a universe, life as we know it might be impossible. Conversely, in a universe with weaker gravity, stars may never form and planets might never accumulate, resulting in a lifeless, barren void. What's even more fascinating is the potential behavior of dark energy in these hypothetical universes. In some, it could be so repulsive that atoms would never form. Solid matter would be an impossibility. On the flip side, a universe where dark energy does not exist or behaves in an entirely different way could experience a state of eternal stasis, or perhaps endless cycles of collapse and rebirth, a cosmic phoenix. Such musings push the very boundaries of our comprehension, forcing us to rethink the fundamental assumptions about the nature of existence. Imagining these radically different universes helps us appreciate the delicate conditions that made life possible in our own. It serves as a profound reminder that the universe we inhabit, with its exact laws and constants, may not be the only one, and that our reality could just be one thread in an endless tapestry of possibilities. In the intricate dance of the cosmos, there exist phenomena that defy easy understanding, pointing to a universe far more mysterious and fine-tuned than we can imagine. Among these is the enigmatic dark flow, a cosmic puzzle that invites deeper reflection on the very nature of our universe and its existence. This mystery, first uncovered by astronomers in 2008, involves the peculiar motion of galaxy clusters that are moving at a staggering velocity, around 1 million miles per hour, toward a distant patch of sky near the constellations Centaurus and Hydra. The fascinating aspect of this movement is that it contradicts the expected random dispersal patterns we would anticipate from gravitational forces and the cosmic microwave background radiation, the faint afterglow of the Big Bang. This is where things get truly intriguing. Could there be more beyond our observable universe, more than we have ever thought to imagine? Some scientists propose that the dark flow might be influenced by gravitational forces exerted by objects beyond the observable cosmos, hinting at the possible existence of parallel universes or even a larger multiversal structure. If our universe is just one of many bubbles in a much larger cosmic expanse, then these structures could be exerting a pull on the galaxies, causing them to flow in an unexpected direction. This idea propels us into speculative but thought-provoking territory, suggesting that our universe, vast though it may seem, is just a small piece of a larger, more complex cosmic reality. While definitive proof remains elusive, the dark flow challenges the boundaries of our knowledge and invites us to consider the far-reaching implications of the multiverse theory. What if there are countless other universes, each with its own laws of physics, each contributing to the grand cosmic symphony that we are only beginning to hear? Such speculation moves us beyond the limits of what we can observe, expanding our imagination to embrace a reality far grander than we have ever conceived. But the dark flow is not the only strange and thought-provoking concept that forces us to reimagine our place in the cosmos. Enter the Big Bounce theory, an alternative to the widely accepted Big Bang model. According to the Big Bounce, our universe is not a singular event that began in a moment of creation, but part of an eternal cycle of expansions and contractions. The theory suggests that after the Big Bang, the universe expands for billions of years before gravitational forces slow the process, eventually leading to a contraction, a big crunch. But rather than ending in a singularity, this contraction reaches a critical point, triggering a cosmic rebound, a new Big Bang, and the birth of another universe. This cycle, according to the Big Bounce hypothesis, continues forever. Birth, expansion, contraction, and rebirth in an endless loop. It's a breathtaking idea, and one that melds the complex worlds of quantum mechanics and general relativity. At the moment of maximum contraction, quantum gravitational effects could prevent the universe from collapsing completely into a singularity. Instead, they could generate a repulsive force, providing the necessary energy to initiate the next cycle of expansion. If the Big Bounce theory is correct, remnants of previous cycles could be encoded in subtle variations in the cosmic microwave background radiation or in the patterns of gravitational waves, offering us a glimpse into the universe's pre-bounce state. This cyclical vision of the universe presents an alternate perspective on existence, one in which time itself becomes cyclical, never-ending. Each cosmic cycle could reset the stage for a new beginning, offering profound implications not only for cosmology, but also for our understanding of time, space, and the fundamental forces that govern the universe. It challenges the linear timeline of the universe, proposing a universe in which endings are only new beginnings, and each cycle carries echoes of the ones before it. Then there's the pyrotic model, which represents an even more radical departure from traditional cosmological theories. Rooted in the principles of string theory, it suggests that our universe emerged not from a singular Big Bang, but from the collision of higher dimensional objects known as brains. These branes exist within a larger, multi-dimensional space known as the bulk. According to this model, our three-dimensional universe is just one of many branes that float through the bulk, and periodically these branes collide, releasing enormous energy that sparks a new Big Bang, creating a new universe. This concept challenges our understanding of cosmic inflation, the theory that the universe rapidly expanded in the moments following the Big Bang, smoothing out any irregularities. Instead, the pyrotic model posits that the high temperatures and densities prior to the collision naturally wholly homogenized the universe. The collision itself provides the impetus for the next stage of cosmic expansion. The pyrotic model also opens the door to the possibility of parallel universes, each existing on its own brane, only a slight nudge away from our own. These alternate universes could have entirely different physical laws, raising questions about the nature of reality itself. Testing the pyrotic model involves searching for distinct patterns in the cosmic microwave background radiation or gravitational waves that could reveal traces of past collisions. By studying these cosmic imprints, scientists hope to uncover a deeper understanding of the nature of the cosmos and its origins. Could the universe we inhabit be just one of many, each spawned by a cataclysmic collision between higher dimensional branes? It's a mind-bending thought that challenges the limits of our imagination and our scientific knowledge, offering new ways of thinking about our existence in the universe. Lastly, we turn to string theory itself, which underpins many of these speculative models. At its core, string theory proposes that the fundamental building blocks of the universe are not tiny, indivisible particles, but rather one-dimensional strings of energy that vibrate in different modes. These strings create the particles and forces we observe, from gravity to electromagnetism to the strong and weak nuclear forces. The true beauty of string theory lies in its potential to unite the four fundamental forces of nature, forces that have long been thought to exist independently of one another, into a single harmonious framework. String theory bridges the worlds of quantum mechanics, which describes the behavior of particles at the smallest scales, and general relativity, which governs the behavior of gravity and space-time at the largest scales. By uniting these two realms, string theory offers a powerful way to explore the deepest mysteries of the universe and provides a theoretical foundation for many of the other models discussed. If string theory is the key to understanding the fundamental nature of reality, then it may one day reveal truths that completely transform our understanding of the universe. One of the most fascinating and intricate elements of string theory is its demand for additional spatial dimensions, dimensions beyond the familiar three we experience every day, plus time. In most models of string theory, there are 10 or even 11 dimensions, with these extra dimensions being compactified or curled up so tightly that they are imperceptible to us at human scales. This peculiar characteristic of string theory allows it to incorporate gravity in a way that is natural and consistent, unlike the struggles faced by quantum field theories. These theories, when trying to quantize gravity, often lead to nonsensical infinities. In contrast, the extended framework of string theory allows for the inclusion of the graviton, a hypothetical quantum particle that represents gravity, arising from a specific vibrational mode of a string. But string theory doesn't stop there. It introduces another revolutionary concept: supersymmetry. This concept suggests that every known particle in the universe has a superpartner particle, a companion that shares certain properties but differs in others. This idea isn't just a theoretical fancy. It addresses crucial problems in physics, such as the hierarchy problem, and helps to make the unification of all forces in nature more seamless and elegant. Despite its intellectual beauty, string theory faces significant challenges in experimental verification. Direct evidence for strings or the existence of these extra dimensions is currently beyond our technological reach, placing it in the realm of speculation for now. However, the mathematical elegance of string theory and its potential to unify the four fundamental forces of nature — gravity, electromagnetism, the weak nuclear force, and the strong nuclear force — offers a tantalizing glimpse into a reality where the diversity of all physical phenomena might simply be manifestations of a single, unified essence. This exploration could eventually lead to a theory of everything, one that ties together the grand tapestry of the universe, forever changing our understanding of reality. In parallel with string theory, there exists another ambitious framework, loop quantum gravity, LQG. This cutting-edge theoretical approach aims to bridge the gap between quantum mechanics and general relativity, two pillars of modern physics that have until now stubbornly refused to coexist harmoniously. Traditional views of space-time, as formulated by Albert Einstein, depict it as a smooth, continuous fabric that warps in response to mass and energy. LQG challenges this idea by suggesting that space-time is fundamentally discrete, composed of tiny quantized loops known as spin networks or spin foam. These loops are incredibly small, on the scale of the Planck length, around 10 to the minus 35 meters, far smaller than anything we can currently observe. The granularity of spacetime in LQG means that at the most microscopic scales, the smooth geometry we take for granted breaks down into a network of interconnected loops resembling a finely woven fabric. This discrete structure is key to LQG's ability to bypass the singularities and infinities that plague general relativity when applied to quantum scales, such as those at the heart of black holes or the earliest moments of the universe. Instead of a singularity, LQG predicts a quantum bounce, where the extreme curvature of spacetime leads to a new expanding phase, reminiscent of, but distinct from, the Big Bounce theory. Perhaps one of the most compelling aspects of LQG is its potential to offer insights into the quantum properties of black holes, including one of the most perplexing puzzles in physics, the preservation of information. This addresses the famous black hole information paradox, a problem that challenges our understanding of the fundamental laws of physics. LQG's ability to quantify areas and volumes in discrete units provides a framework for calculating black hole entropy in a manner that aligns with the holographic principle, a concept that suggests our universe is a projection of information stored on a distant surface. While still in its infancy and facing significant experimental hurdles, loop quantum gravity offers a radically new perspective on the nature of space-time, pushing the boundaries of physics and our understanding of the universe. Lastly, the Anthropic principle introduces a provocative idea that the universe seems finely tuned to support life, especially human life. It suggests that the physical constants of the universe, the laws of nature, and the very conditions of existence may be precisely calibrated in such a way that life could emerge. This concept pushes us to question the relationship between the cosmos and our place within it, offering profound implications for understanding the structure of reality itself. As we explore these cutting-edge theories, we may be on the verge of unlocking the deepest secrets of existence, revealing the underlying unity that connects everything in the universe. The principle asserts that the physical universe must be compatible with the conscious beings who observe it, suggesting that the universe's laws, constants, and fundamental parameters are finely tuned to allow for the emergence of life. Essentially, this principle argues that if the universe were any different, we wouldn't be here to observe it. The Anthropic principle, as it's called, comes in two distinct forms: the weak and the strong Anthropic principles. The weak Anthropic principle suggests that the universe's observed values of physical constants aren't particularly surprising. Why? Because only those values that permit the existence of observers, like us, can actually be observed. To put it simply, if the gravitational constant were weaker or stronger by even a small fraction, galaxies, stars, and planets might never have formed. Without such formations, life as we know it would be impossible. Therefore, it's not particularly astonishing that we find ourselves in a universe with the exact conditions necessary for our existence. We simply couldn't exist in a universe with any other setup. On the other hand, the strong Anthropic principle ventures into more profound territory. It proposes that the universe must have properties that allow life to develop at some stage in its history. This suggests, in a sense, that the cosmos is somehow designed with life in mind. This version of the principle raises deeper philosophical and metaphysical questions. Is our universe just one of many, each with different constants and laws, as suggested by the multiverse theory? Or could there be some greater design, some higher purpose at work? These questions plunge us into the very heart of existence itself. Is the alignment of conditions that allow life just a fortunate accident in an infinite sea of possible realities? Or is it something more? While the anthropic principle itself isn't a scientific explanation in its own right, it forces us to grapple with the significance of the parameters that govern our cosmos. It challenges both scientists and philosophers to explore why the universe exists the way it does, and whether our very existence is a coincidence or part of a larger, more intricate design. In a parallel universe of inquiry, we encounter the modified Newtonian dynamics M-Ohm theory, a novel framework proposed by physicist Mordechai Milgrom in the early 1980s as an alternative to the dark matter hypothesis. Dark matter was introduced to explain a series of astronomical puzzles, such as the anomalous rotational speeds of galaxies that couldn't be explained solely by the visible matter we observe and Newton's laws of gravity. Instead of invoking an unseen, invisible form of matter, Mond posits that the laws of gravity themselves might be different, but only at very low accelerations, specifically in the outskirts of galaxies. In Mond, Newton's classical laws of gravity are modified when the acceleration due to gravity falls below a threshold of approximately 0.01 nanometers per second squared. At these extremely low accelerations, the force of gravity doesn't diminish with the square of the distance as Newton's law dictates. Instead, it follows a weaker inverse linear law. This adjustment offers an explanation for the flat rotation curves of galaxies, removing the need for dark matter. In Mond's model, the rotational speeds of stars at the edges of galaxies can align with the visible matter present when this modified gravity law is applied. However, as intriguing as Mond is, it faces significant challenges. While it successfully addresses the flat rotation curves of galaxies, it struggles to explain other phenomena commonly attributed to dark matter. For instance, it doesn't fully account for gravitational lensing observed in galaxy clusters or the large-scale structure of the universe. Therefore, while Mond presents an intriguing alternative, the debate continues, and it's clear that both the anthropic principle and alternative gravitational models like Mond leave us pondering the deeper mysteries of the cosmos. Could there be more to the universe than what we can see or measure? And are we truly just observers in a random cosmos, or is there a greater story unfolding? In the search for a deeper understanding of the cosmos, one of the most challenging and exciting frontiers is the reconciliation of general relativity with emerging theories such as modified gravity, M. Despite facing hurdles, especially in its ability to fully describe cosmological phenomena like the cosmic microwave background radiation, M remains a dynamic area of research. It has sparked numerous hybrid models, such as relativistic M and tensor scalar vector gravity, TSVG, which aim to bridge the gap between theoretical predictions and observed cosmic events. These theories are not merely academic exercises. They offer profound insights that could reshape our understanding of gravity itself. By questioning the foundational laws of gravity, M invites us to reconsider our view of the universe. Could these new approaches help unravel the dark matter enigma, or perhaps lead us to a more comprehensive theory of gravity? This is a thrilling possibility, one that could have far-reaching implications. Among the most compelling aspects of M is its potential to unlock the mysteries of dark matter, a substance that constitutes about 27% of the universe's energy content. While traditional theories lean on hypothetical particles like weakly interacting massive particles, IMPs, the exploration of gravitationally driven models may provide a revolutionary alternative. In parallel with the search for answers to dark matter, another fascinating theory is gaining momentum: the concept of primordial black holes, PBHs. These intriguing objects, if they exist, could completely transform our understanding of the early universe. Unlike conventional black holes, which form from the collapse of massive stars, PBHs could have formed in the first moments after the Big Bang. The idea is that tiny fluctuations in the incredibly dense and hot early universe might have been strong enough to trigger gravitational collapse, forming black holes with masses ranging from microscopic to many times that of the Sun. PBHs are controversial, yet they hold the potential to explain several cosmic mysteries, particularly dark matter. Because they are purely gravitational objects, PBHs could be responsible for some or all of the dark matter that eludes detection through conventional particle-based theories. Imagine if these ancient black holes are the missing piece in understanding the elusive nature of dark matter. Their presence might also provide the key to understanding how galaxies and large-scale structures formed. With their gravitational pull, PBHs could serve as seeds for the creation of galaxies, influencing the overall structure of the universe. Furthermore, the detection of gravitational waves, particularly those observed by LIGO and Virgo, could offer another clue to the existence of PBHs. Some of these signals involve the merging of black holes with unusual masses, which might be linked to PBHs. Beyond these intriguing connections, the study of PBHs touches on the very nature of quantum gravity, a theory that seeks to unify the laws of quantum mechanics and general relativity. If PBHs were formed under the extreme conditions of the early universe, they might carry signatures from a time long before we had the technology to probe such high-energy environments. These imprints could provide essential clues about the physics that govern the universe just after the Big Bang, insights that are currently beyond the reach of our particle accelerators. While the evidence for PBHs remains indirect, their potential to reshape our understanding of the universe makes them a captivating topic of study. Even if these objects are never directly detected, the very pursuit of their existence challenges our preconceptions and pushes the boundaries of cosmology. It is through the study of such enigmatic phenomena that we inch closer to solving the deepest mysteries of the universe. Equally fascinating is the concept of baryon asymmetry, which addresses one of the most profound questions in both cosmology and particle physics. Why is there so much more matter than antimatter in the observable universe? According to the standard model of particle physics, the Big Bang should have produced equal amounts of matter and antimatter. When these two opposites collide, they annihilate each other, leaving only energy behind. Yet, we observe a universe dominated by matter, with antimatter appearing to be almost completely absent. This imbalance, known as baryon asymmetry, is fundamental to our existence. If matter and antimatter had been produced in perfectly equal quantities, they would have annihilated each other, and the universe would be filled only with radiation. The fact that this did not happen implies that early in the universe's history, there was a slight excess of matter over antimatter. Specifically, 1 extra baryon for every billion baryon-antibaryon pairs. This small difference is what allowed matter to survive and form galaxies, stars, and planets. To understand baryon asymmetry, scientists have proposed several mechanisms, such as the involvement of the Higgs boson or hypothetical particles like axions or sterile neutrinos. Furthermore, the phenomenon of CP violation, where certain particle interactions violate symmetry between matter and antimatter, has been observed, but not to the extent needed to explain the observed matter-antimatter imbalance. The search for a deeper understanding of baryon asymmetry is more than an academic pursuit. It is critical to understanding the fundamental forces that shape the universe and continue to govern it. The significance of baryon asymmetry extends far beyond just explaining why the universe is made of matter. It holds profound implications for the early universe's conditions and may offer insights into physics beyond the standard model. In this search for answers, we are not only investigating the origins of the universe itself, but also the very nature of the fundamental forces that govern all of existence. This inquiry could lead to the discovery of new particles, new forces, and a deeper understanding of the laws that bind our cosmos together. Ultimately, both primordial black holes and baryon asymmetry represent key pieces in the puzzle of the universe's origins and evolution. Each offers a window into the forces that shape the cosmos and continues to influence its structure and behavior. As research continues in these areas, we are bound to uncover more revelations that will challenge our understanding of the universe, inviting us to explore the deepest questions about existence itself. As we continue to explore the profound mysteries of the universe, each step brings us closer to unraveling the enigma that lies at the very core of our existence. Through groundbreaking experiments conducted in particle accelerators, meticulous observations of cosmic microwave background radiation, and the study of high-energy astrophysical phenomena, we are gradually peeling back the layers of the cosmos. Each discovery deepens our understanding. Yet still, the ultimate question remains: Why does the universe, in its vast and infinite complexity, exist at all? One of the most tantalizing concepts emerging from modern cosmology is the holographic universe theory. This theory suggests that the three-dimensional universe we experience, its space, time, and all that resides within it, might not be as it appears. Instead, it could be an illusion, projected from a two-dimensional surface far beyond our perception. This fascinating hypothesis finds its roots in the work of physicist Gerard 't Hooft in the 1990s, later expanded upon by Leonard Susskind. Their ideas proposed a new way to look at reality, suggesting that the very fabric of space-time, all particles, forces, and perhaps even the laws of physics themselves, may originate from information inscribed on a distant cosmological boundary. To better understand this, imagine a hologram. It is a two-dimensional image, yet it encodes three-dimensional information. The holographic universe theory contends that, in a similar fashion, the universe we observe could be the projection of data etched onto a flat, two-dimensional surface, much like a holographic image is. This is more than just a curious concept. It is a profound rethinking of the nature of reality itself. Recent advancements in the study of black holes have provided further support for this idea. When matter falls into a black hole, the information about that matter isn't lost, but rather encoded onto the event horizon, a two-dimensional boundary. This process, known as holographic encoding, suggests that the universe too could work along similar lines. Entropy and information theory further enrich this hypothesis. In essence, these theories propose that the amount of information a region of space can hold is not based on its volume, but on its surface area. This means that despite the three-dimensional reality we live in, the underlying structure of the universe might be governed by principles derived from a flat, two-dimensional realm. Such ideas challenge everything we thought we knew about the cosmos, inviting us to see the universe through a radically different lens. Imagine life on a planet orbiting a pulsar, an environment that would be anything but familiar. Pulsars, the remnants of supernova explosions, are highly magnetized neutron stars that spin rapidly and emit beams of electromagnetic radiation from their magnetic poles. These beams, akin to cosmic lighthouses, sweep through space, and their radiation is extraordinarily intense. Any planet situated near such a pulsar would face a constant bombardment of high-energy gamma rays and X-rays, creating an atmosphere so hostile that life, as we understand it, would seem impossible. Yet this doesn't mean that life would be entirely out of the question. While the conditions around a pulsar would be lethal to most forms of life, hypothetical life forms could adapt in extraordinary ways. Shielding mechanisms would be crucial for survival. For instance, life could exist deep below the planet's surface, similar to extremophiles on Earth that thrive in the deepest parts of the ocean or miles underground, far from the reach of harmful radiation. Additionally, the planet would need an incredibly thick atmosphere or a powerful magnetic field to deflect much of the pulsar's radiation. This dense atmosphere could be composed of heavy gases, acting as a protective shield to absorb much of the harmful radiation before it reaches the surface. In this hostile environment, life might follow rhythms synchronized with the pulsar's periodic emissions. These pulsations, ranging from milliseconds to several seconds, would send waves of energy crashing against the planet's atmosphere and magnetic fields, creating volatile and dynamic conditions. Adaptations in these life forms might include exceptional radiation resistance, advanced DNA repair mechanisms, and life cycles that align with periods of lower radiation intensity. Though speculative, such adaptations would reflect the resilience and ingenuity of life forms that could survive in one of the most extreme environments known to us. These scenarios, although hypothetical, highlight the remarkable adaptability of life and the potential for survival in the most unlikely of places. As we continue to study the universe's most extreme environments, we expand the boundaries of what we understand about life, existence, and the cosmos itself. The universe is not just a vast expanse of space, it is an ever-unfolding mystery, rich with possibilities and wonders we have only begun to comprehend. A tidally locked planet where one side is perpetually bathed in daylight while the opposite side is trapped in eternal darkness presents a unique and fascinating environment. This configuration, often seen in certain exoplanets, creates an intricate web of ecosystems and climates that could potentially support life in ways we are just beginning to imagine. In such a world, the planet's day side, continuously exposed to its stars' intense rays, would experience constant daylight. The result is an environment with extreme, unrelenting heat that could push life forms to adapt in highly specialized ways. Organisms on the day side might evolve extraordinary features like heat-resistant exoskeletons, reflective surfaces, or the ability to dissipate heat efficiently, much like the desert-dwelling creatures on Earth. Additionally, life might be concentrated in regions where reflective surfaces, such as ice caps or desert sands, help lower temperatures. These microenvironments could create habitable zones where life could thrive, albeit with challenges posed by the erratic temperature fluctuations. Photosynthetic organisms, in particular, might adapt to the uninterrupted sunlight, evolving strategies to store energy and regulate growth even in the face of resource scarcity. Some could develop the ability to endure extreme heat, while others might evolve to store energy during the sunlit hours, conserving it for the cooler periods. These organisms would likely be at the heart of a food chain that sustains diverse forms of life, each uniquely adapted to their hot, sun-drenched environment. On the opposite side of the planet, a stark contrast to the blazing day side, the night side would exist in a perpetual state of darkness and extreme cold. Here, life forms might not rely on the energy of the sun at all. Instead, they would adapt to survive using alternative methods, such as chemosynthesis or tapping into geothermal energy. This could be similar to the extremophiles found near deep-sea hydrothermal vents on Earth, thriving in environments where no sunlight reaches. Life forms here could develop unique traits such as bioluminescence, which could serve multiple purposes, lighting up the eternal night, attracting mates, or luring prey in the darkness. However, it is the twilight zone, the narrow temperate band between the day and night sides, that may hold the most promise for life. This zone would likely experience relatively stable, mild temperatures and could host a rich diversity of life forms, each adapting to this unique environment. Some organisms might thrive in the twilight itself, basking in the soft glow, while others might venture into the extremes, gathering resources from the scorching daylight or the freezing night side. The twilight zone could harbor an ecosystem with complex, highly specialized organisms, creating a dynamic balance where life could not only survive, but flourish. The conditions on a tidally locked planet could foster an array of adaptive life forms, leading to a biological tapestry as intricate and fascinating as those found in the most extreme environments on Earth. Hot Jupiters, a class of exoplanets that orbit perilously close to their parent stars, present a whole new set of mysteries that have expanded our understanding of planetary science. These gas giants, similar in size and composition to Jupiter in our own solar system, orbit their stars in a matter of days, instead of the years it takes for planets like Earth to complete an orbit. The heat generated by their proximity to their star can reach blistering temperatures, often soaring into the thousands of degrees Fahrenheit, hence the name Hot Jupiters. When hot Jupiters were first discovered, they challenged conventional models of planetary formation. According to the widely accepted theory, gas giants like Jupiter form in the cooler outer regions of a protoplanetary disk, far away from the intense heat of a young star. However, the discovery of gas giants in such close orbits around their stars suggested something unusual. Either these planets formed differently, or they migrated inward after their formation. Current theories about the formation of hot Jupiters hypothesize that these planets might have initially formed in the colder outer regions of their star systems, only to migrate inward later in their development. This migration could happen through a variety of mechanisms. One theory suggests that gravitational interactions between the forming planets and the protoplanetary disk could cause the hot Jupiter to spiral inward toward the star. Another possibility involves interactions with a secondary star in a binary system, which could perturb the orbit of the gas giant, pushing it closer to its primary star. For this migration to occur, it must happen quickly, or the gas giant risks being pulled into the star or disrupted by its immense gravitational forces. Hot Jupiters have not only broadened our understanding of planetary systems, but have also forced astronomers to reconsider the processes behind planetary formation and evolution. These planets highlight the complexity of the universe and the unexpected pathways that planetary bodies can take on their journey through space. The study of hot Jupiters continues to refine our models of how planets grow, evolve, and interact with their stars, offering a glimpse into the dynamic and ever-changing nature of planetary systems across the cosmos. Super-Earths are an intriguing category of exoplanets that have captivated the attention of scientists and astronomers ever since their discovery. These planets, larger than Earth but considerably smaller than the ice giants Uranus and Neptune, occupy a fascinating niche in the realm of planetary science. Ranging from just over Earth's size to 10 times its mass, super-Earths push the boundaries of our understanding about the diversity of planets and the conditions that might support life. These planets present a new class of worlds that sit between terrestrial planets like Earth and gas giants such as Jupiter. Super-Earths often possess thick, dense atmospheres, dynamic geological activity, and potentially vast oceans. Their increased mass results in stronger gravitational fields that can help them retain thicker atmospheres, creating more stable climates over long periods of time. This stability is a key factor in making these planets potentially more habitable, as they may foster conditions conducive to life. Their size can also promote tectonic activity, an essential process for recycling elements necessary for life and sustaining habitability on geological timescales. What makes super-Earths even more captivating is how they stretch the concept of the habitable zone. Traditionally, the habitable zone, the region around a star where liquid water can exist, has been seen as a narrow band of possible locations for life-supporting planets. However, some super-Earths might have the right conditions for life even if they reside outside this zone. The key to this potential habitability lies in their ability to generate internal heat, either through tidal forces caused by their moons or through radiogenic decay. This heat could sustain subsurface oceans, similar to the ones speculated to exist on moons like Europa and Enceladus in our own solar system. By expanding our definition of the habitable zone, super-Earths provide tantalizing possibilities for life beyond Earth, suggesting that habitable planets might be more common than previously thought. Furthermore, these planets offer a unique opportunity for astronomers to refine their models of planetary formation and evolution. By studying their atmospheres, compositions, and orbital dynamics, scientists can gain valuable insights into how planets form, accumulate material, and interact with their parent stars and neighboring planets. The diversity of super-Earths orbiting various types of stars, from stable G-type stars like our Sun to the more volatile M dwarfs, adds another layer of complexity to our understanding of planetary systems, offering exciting possibilities for future exploration and the search for extraterrestrial life. But as we look further out into the solar system, we find ourselves faced with even more mysterious giants, the ice giants Uranus and Neptune. These distant worlds, unlike the gas giants Jupiter and Saturn, are composed not just of hydrogen and helium, but of heavier elements like water, ammonia, and methane. These elements form complex layers of icy and rocky materials beneath thick atmospheres, making these planets crucial to our understanding of how planets evolve and what materials are required for their formation. One of the greatest puzzles surrounding Uranus and Neptune is their formation. Current models suggest that these planets formed further out in the protoplanetary disk, where icy and rocky materials were more abundant. But the exact process remains a mystery. Some scientists hypothesize that Uranus and Neptune may have initially formed as smaller cores that slowly accumulated icy and rocky material over time. Others suggest that they underwent rapid accretion, capturing significant amounts of gas and ice before migrating inward to their current positions in the outer solar system. The idea of planetary migration is particularly compelling, as it suggests that these planets could have undergone significant orbital shifts, potentially reshaping the early solar system and influencing the formation of other celestial bodies. Furthermore, Uranus and Neptune have magnetic fields that behave in ways that set them apart from other planets in our solar system. Unlike Earth, Jupiter, or Saturn, whose magnetic fields align closely with their rotational axes, Uranus and Neptune exhibit tilted, offset magnetic fields. This anomaly points to a complex internal structure, possibly involving convecting layers of ionically conductive fluids, rather than the metallic hydrogen cores seen in the gas giants. Uranus's extreme axial tilt, basically lying on its side, has led scientists to propose that a massive collision in its distant past could explain this unusual feature. The weather patterns on these distant worlds are no less intriguing. For instance, Neptune, despite receiving far less sunlight than Earth, boasts the strongest winds in the entire solar system. The mechanisms driving these extreme wind speeds and the energy sources that power such dynamic atmospheres are still poorly understood. Examining these phenomena can yield profound insights into the processes that govern atmospheric dynamics, not just on Earth, but on other worlds as well. Studying ice giants like Uranus and Neptune is more than just a quest for knowledge about our solar system. Their study allows us to draw comparisons with exoplanets of similar sizes and compositions, offering broader insights into planetary systems beyond our own. By probing their magnetic fields, atmospheric compositions, and internal structures, we unlock the mysteries of planetary formation, migration, and evolution. Insights that have implications far beyond the limits of our solar system. In sum, both super-Earths and ice giants push the boundaries of our understanding of the cosmos. They provide clues about the formation and evolution of planets, the potential for habitability, and the intricate dynamics that govern planetary systems. As we continue to study these fascinating worlds, we uncover not just the secrets of our solar system, but also the broader narratives of planetary genesis and evolution that stretch across the universe. Ocean planets, those vast celestial bodies entirely covered in water, present an extraordinary possibility for the existence of life. Imagine a world where oceans stretch endlessly, from shallow seas to depths that could reach hundreds of kilometers below the surface. On such planets, life could not only survive, but potentially thrive, adapting to conditions far different from our Earth. This tantalizing prospect sparks a sense of wonder and exploration, as scientists speculate on the incredible environments these planets might harbor. Water, the universal solvent, is one of the most crucial elements that could make an ocean planet suitable for life. Its ability to facilitate a range of chemical reactions is essential for the development of life as we know it. Even though the extreme pressures of deep ocean environments might seem unwelcoming, life forms could still flourish, much like the extremophiles that thrive in Earth's deep-sea hydrothermal vents. These resilient organisms derive energy not from sunlight, but from the rich, superheated water emitted by the vents, a process that could very well be mirrored on ocean planets. Geothermal vents on these planets might provide the vital energy and nutrients needed to sustain thriving ecosystems of microorganisms, forming the foundation for more complex life forms to evolve. One of the most fascinating aspects of ocean planets is their potential to regulate their climates. Water's ability to store and circulate immense amounts of heat could buffer drastic temperature fluctuations, ensuring a stable environment. If the planet possesses an atmosphere rich in greenhouse gases, the temperature stability could be further enhanced, making it a more conducive environment for life. In addition, an active water cycle, through the evaporation and precipitation of water, could foster the distribution of essential nutrients across the planet's oceans. This cycle would enrich the entire water column, ensuring that every level of the ocean is infused with the necessary elements for life to thrive. While life on ocean planets may seem predominantly suited to the depths, the regions closer to the surface, where sunlight can penetrate, could host thriving photosynthetic organisms. These organisms would form the foundation for complex food webs, much like those on Earth. The distribution of light energy and nutrients would determine the biodiversity of these worlds, creating rich ecosystems that span from the surface to the ocean floor. The interplay between solar energy at the surface and geothermal energy from the depths could give rise to banded ecosystems, each with its own unique forms of life, evolving along separate pathways. This suggests that the diversity of life on ocean planets could be astonishing, from simple microorganisms to potentially more sophisticated multicellular creatures. In addition to the potential of ocean planets themselves, the search for extraterrestrial life has found a promising avenue in exoplanets that orbit red dwarf stars. These stars, though small and cooler than our Sun, are the most common in our galaxy, making them prime targets in the search for habitable planets. Red dwarf stars can support planets with liquid water, a critical ingredient for life. The unique conditions surrounding these stars suggest that exoplanets in their habitable zones could possess environments where life could emerge. To detect signs of life on such exoplanets, scientists examine a range of factors, including atmospheric composition, surface conditions, and the possibility of biological processes. One of the most exciting biosignatures is the presence of specific gases such as oxygen and ozone in an exoplanet's atmosphere. On Earth, these gases are byproducts of photosynthetic life, making their detection a strong indicator of biological activity. However, the conditions around red dwarf stars might present different challenges. Gases like methane and nitrous oxide, which could be produced through both geological and biological processes, become especially intriguing in the search for life. When these gases appear in balance with oxygen, they offer compelling evidence of biological processes that could indicate the presence of life. Through the exploration of ocean planets and exoplanets orbiting red dwarf stars, we expand our understanding of the many ways life might exist across the universe. These distant worlds could harbor ecosystems unlike anything we've encountered, and the search for biosignatures in their atmospheres may one day reveal the presence of life forms that are entirely alien, yet undeniably similar in their dependence on water. The universe, teeming with oceans and alien biospheres, beckons with the promise of discovery. Imagine a world far from our own, orbiting a red dwarf star, where microbial activity and atmospheric chemistry are providing the first hints of life beyond Earth. This distant exoplanet could host an environment where life as we know it, or something entirely foreign, might thrive. Among the key indicators that scientists search for when investigating exoplanets are the chemical signatures left by gases like nitrous oxide, a byproduct of microbial life here on Earth. If detected on an exoplanet, this gas could be one of the strongest clues pointing to biological activity. However, detecting gases is only the beginning. The behavior and stability of these gases in a planet's atmosphere are just as critical. Red dwarf stars, which are known for their unpredictable stellar flares and variability, can wreak havoc on a planet's atmosphere. These eruptions release massive bursts of radiation that could destabilize the delicate chemical balance that life needs to survive. Despite these challenges, if scientists find persistent or stable levels of biosignature gases, it could point to a biological source replenishing these compounds. Much like Earth's ecosystems constantly recycle gases like oxygen and nitrogen. Telescopes like the James Webb Space Telescope are essential tools in this pursuit. With their advanced spectrometry capabilities, these instruments can peer across light years, examining the atmospheres of distant worlds for these crucial chemical markers. But the hunt for life doesn't end with atmospheric chemistry. The surface conditions of a planet play an equally important role. Planets with stable liquid water, whether oceans, lakes, or even subsurface aquifers, are prime candidates for supporting life, as water is the fundamental solvent for life's biochemical processes. The presence of tidal forces from a red dwarf star could provide even more clues. These forces, caused by the gravitational pull between the planet and its star, could trigger intense geothermal activity beneath the surface. This geothermal heat could create environments similar to Earth's hydrothermal vents, where unique ecosystems have flourished without sunlight, relying on chemical energy instead. Moreover, life forms might evolve to harness the infrared light emitted by their star, adapting their photosynthetic processes to a different wavelength than those found on Earth. In this case, surface life forms would be tailored to the unique energy spectrum of their host star, further diversifying the potential ways life could exist beyond Earth. But what about planets with an entirely different atmosphere? Consider a planet with a thick, hydrogen-rich atmosphere. Such an environment opens up a fascinating frontier for the potential of exotic life forms. Unlike Earth's nitrogen and oxygen-rich atmosphere, a hydrogen-dominated atmosphere would present an entirely different set of chemical and physical conditions. This difference doesn't rule out life. In fact, it might suggest entirely new biochemistries. Hydrogen, being a lightweight molecule, is a potent greenhouse gas. This property means that even a planet far from its star could maintain temperatures warm enough to sustain liquid water, a crucial ingredient for life as we understand it. Some theoretical models propose that on such planets, hydrogen could act as a thermostat, keeping the planet's surface comfortably warm despite its distance from the star. This stability could enable the development of biochemistries that we haven't even begun to imagine. For example, organisms on such a world might utilize hydrogen to fuel metabolic processes, much like the bacteria on Earth that use hydrogen in chemosynthesis. Rather than relying on oxygen-based metabolism, these hypothetical life forms could exploit hydrogen as a vital source of energy, creating a completely new form of life that thrives in a hydrogen-rich environment. Extremophiles on Earth already demonstrate how life can adapt to environments rich in hydrogen. Methanogens, for instance, produce methane by reacting hydrogen with carbon dioxide, a process that could easily be replicated on distant exoplanets. In addition to these biological processes, a hydrogen-rich atmosphere could also create the right conditions for the formation of complex organic chemistry. With the presence of carbon, nitrogen, and oxygen, fascinating organic compounds could form, leading to life forms with metabolisms and structures that are vastly different from anything on Earth. This opens up a world of possibilities, where the building blocks of life could be shaped by conditions that are unfamiliar but equally viable. In conclusion, while the unique characteristics of red dwarf systems and hydrogen-dominated atmospheres present formidable challenges, they also provide some of the most promising clues in the search for extraterrestrial life. By studying the composition of exoplanet atmospheres, surface conditions, and biological processes, we move one step closer to answering one of humanity's most profound questions. Are we alone in the universe? In the vast expanse of the universe, life may take forms that defy our deepest expectations. These life forms could harness hydrogen in ways so alien, so beyond our current understanding, that they might engage in biochemistries entirely different from anything we know. The presence of hydrogen-rich atmospheres could lead to ecosystems where the dynamics of life are reshaped in ways we can scarcely imagine. Without the threat of oxidative stress from oxygen, organisms could evolve entirely new defensive mechanisms, preparing them to withstand the harshest environmental stresses, radiation, extreme temperatures, or even factors we have yet to comprehend. Imagine a world where community structures are based on hydrogen-based energy cycles, where nutrients flow in patterns foreign to our earthbound understanding. Such a biosphere might seem strange, even unrecognizable, but it could thrive, supported by a delicate balance that sustains life in a radically different environment. The study of these potential worlds challenges our Earth-centric view of life and invites us to broaden our search. We are reminded that life, in its incredible adaptability, may find a way to flourish even in the most extreme alien conditions. The more we learn, the more we realize that life may not need to resemble our own in order to exist. Now picture a planet with an extreme axial tilt, one so dramatically tilted that its seasonal shifts are unlike anything we experience on Earth. Instead of the mild transitions we're accustomed to, this planet would face long, unyielding periods of scorching heat and frigid cold. As the planet orbits its star, one hemisphere would be locked in a permanent summer, with the sun directly overhead for an extended period. The other hemisphere would experience an eternal winter, plunged into darkness and cold. The temperature extremes would be so severe that they could turn the landscape into a desert or a frozen wasteland. Oceans could freeze over, glaciers might advance, and the world would exist in a constant state of flux. For life to persist on such a planet, it would have to be incredibly resourceful. During the endless summer, extreme heat and radiation could create an environment where survival seems impossible, unless moderated by atmospheric conditions or oceans that act as natural buffers. Water would evaporate rapidly, creating massive storms and possibly even hyperhurricanes. Meanwhile, in the dark, frozen winter hemisphere, life would have to adapt to complete darkness and near absolute cold. Organisms might enter states of dormancy, relying on geothermal or other non-solar energy sources to survive. The planet's equinoxes, its spring and autumn, would be times of intense transition, marked by rapid shifts in temperature, massive storms, and floods as ice from the winter hemisphere begins to melt. The equator of this planet could emerge as a potential sanctuary, offering a more stable climate. Its perpetual twilight could provide the mildest temperatures year-round, offering a haven for life. Here, plants and animals would need to be exceptionally adaptable. Flora might evolve to store energy and water, enabling them to survive the extremes of both light and darkness. Rapid reproductive cycles could be the key to thriving in such a dynamic environment. Similarly, animals might migrate vast distances, following the more stable climates, or they might develop hibernation or estivation strategies, allowing them to endure the harsh transitions between seasons. Human or intelligent life on such a planet would face monumental challenges. Engineering solutions would be essential to survive the extremes. Settlements might need to be mobile, shifting between hemispheres as the seasons dictate. Alternatively, enormous underground or insulated habitats could be constructed to shield inhabitants from the extreme heat or cold. A planet with an extreme axial tilt would be a world of stark contrasts, where life would be tested at every turn. The resilience of any life form living there would be constantly challenged, making the ability to adapt not just a necessity, but the very essence of survival. Imagine a world where the very laws of nature are pushed to their limits. A world where the environment is not merely challenging, but so unpredictable that it would demand a life form capable of adapting, surviving, and even thriving in conditions that might seem unimaginable to us. This is the reality faced by exoplanets with elliptical orbits, or eccentric orbits, which present a complex and intriguing puzzle to scientists. Unlike the nearly circular orbits of planets in our solar system, these distant worlds follow elongated paths around their stars, creating wild fluctuations in their proximity to their suns. The result? Drastic shifts in distance and, consequently, extreme changes in temperature and climate. These eccentric orbits don't just challenge our understanding of planetary stability, they force us to reconsider what makes a planet habitable at all. One of the most striking features of planets with such orbits is the wild temperature swings they experience. When a planet is closest to its star, it is bombarded by intense radiation and heat, potentially reaching searing temperatures. This could cause significant atmospheric expansion where gases are stripped away or radically altered. Yet, as the planet swings to the farthest reaches of its orbit, temperatures plummet, possibly leading to freezing conditions. It's a harsh cycle that would test the limits of any atmosphere and its ability to protect life. Such extreme temperature fluctuations place enormous strain on the planet's environment. These shifts could lead to the depletion of crucial elements required for life, like liquid water. A planet in such an orbit would struggle to maintain stable climate conditions, making it difficult for life, as we know it, to exist. After all, liquid water is considered essential for life. The habitable zone around a star, the region where liquid water can exist, becomes far more unpredictable for planets with eccentric orbits. Rather than a steady, life-supporting zone, a planet might only pass through this habitable zone at certain points in its orbit, making conditions highly seasonal in a way we've never observed in our own solar system. The implications for life in such an environment are profound. Organisms would need to endure extremely variable conditions, with long stretches of time potentially devoid of the stable, life-sustaining environments they require. It's a challenge that would push the boundaries of evolutionary resilience. Could life develop the necessary adaptations to survive such erratic shifts? The answer remains uncertain, but the possibility is tantalizing. But that's not the only challenge. Gravitational interactions between the star and its orbiting planet can have a profound impact on the planet's dynamics. As the planet moves along its eccentric path, tidal forces from the star can stretch and squeeze the planet, creating internal friction and generating heat, a process known as tidal heating. This heat could potentially trigger volcanic activity or even create subsurface oceans beneath the planet's surface, offering secluded environments where life might persist despite the planet's harsh surface conditions. Moons orbiting such planets would also feel the impact of these tidal forces, further complicating the dynamics within the planetary system. Perhaps most intriguing of all is the chaotic nature of these systems over long periods. The gravitational forces at play in a multi-body system where several planets interact can lead to unstable orbits that may shift dramatically over time. Eccentric orbits might even be the result of past gravitational encounters with other large celestial bodies, suggesting a history of dynamic rearrangements and planetary migrations. This history could unlock fascinating clues about the evolution of planetary systems, offering a glimpse into the forces that shape them. Despite the challenges, the study of eccentric orbits offers a unique opportunity to explore planetary environments that are unlike anything in our solar system. They push the boundaries of our understanding of what is possible when it comes to habitability, forcing us to consider new factors that could influence a planet's ability to support life. By studying these dynamic systems, scientists gain a deeper understanding of how life could adapt to extreme conditions, how planetary environments evolve, and the gravitational forces that govern the very structure of galaxies. This exploration not only opens up new possibilities for understanding life on distant worlds, but also challenges us to rethink the very nature of life itself. Could life, as we know it, exist in such a volatile environment? Or would it require something far more versatile and resilient, capable of adapting to the most extreme conditions imaginable? In the grand cosmic dance of the universe, it's these eccentric planets, with their chaotic orbits and volatile climates, that offer a fascinating glimpse into the potential for life beyond our own solar system. Each discovery brings us closer to unraveling the mysteries of the universe, as we continue to push the boundaries of what we know about the cosmos. At the heart of a starburst galaxy, dynamic systems give rise to a prolific rate of star formation. The key ingredients? An abundance of gas and dust, the essential raw materials for new stars. Starburst galaxies are often home to vast reservoirs of hydrogen gas, which collapse under their own gravity to form dense molecular clouds. Within these clouds, certain regions become gravitationally unstable, triggering a fragmentation process that leads to the birth of new stars. External events, such as galaxy mergers or close encounters with other galaxies, often catalyze this process. These interactions compress the gas clouds, setting off a chain reaction of star formation by creating shock waves that destabilize molecular clouds, making them ripe for collapse. As new stars emerge, feedback mechanisms within starburst galaxies play a critical role in sustaining the process. The intense radiation emitted by newly formed stars heats the surrounding gas, causing it to expand and compress adjacent clouds, further promoting star formation. Supernova explosions of massive stars also inject enormous amounts of energy into the surrounding medium, stirring up gas and dust, and causing additional regions to collapse, creating more stars. This positive feedback loop can sustain high star formation rates for several million years, a period known as the starburst phase. During this phase, starburst galaxies often exhibit brilliant luminosity. The intense ultraviolet light from the young, massive stars ionizes the surrounding gas, creating regions known as high regions, which shine brightly in optical and infrared wavelengths. The galaxy structure during this time is often complex and chaotic, with clumps of young, hot stars scattered among turbulent gas clouds and dark dust lanes. However, this rapid rate of star formation is not sustainable in the long term. As starburst galaxies exhaust their reservoirs of gas and dust, the rate of star formation eventually declines. Additionally, the energetic processes within starburst phases can drive powerful galactic winds, expelling gas and dust into intergalactic space and depleting the material necessary for future star formation. Over time, the starburst phase subsides and the galaxy may evolve, potentially merging with other galaxies or transitioning into a more quiescent state. Studying these galaxies provides valuable insights into the processes of star formation and galaxy evolution. These cosmic laboratories allow astronomers to observe the extremes of star creation, helping us understand the conditions under which massive bursts of star formation occur. This knowledge not only sheds light on the life cycles of galaxies, but also on the broader mechanisms that govern the evolution of the universe. Active galactic nuclei, AGN, play a profound and multifaceted role in shaping their host galaxies, influencing everything from star formation processes to overall galactic structure. An AGN is a small region at the center of a galaxy that emits an extraordinary amount of energy, primarily due to the accretion of matter onto a supermassive black hole. As matter spirals inward toward the black hole, it forms an accretion disk, heating up and radiating across the electromagnetic spectrum. The intense energy output of the AGN can have far-reaching effects on the host galaxy. One of the most significant influences of an AGN is through the process known as AGN feedback, which can either suppress or enhance star formation within the galaxy. In its more classical form, AGN feedback is often negative. The intense radiation and energetic outflows from the AGN can heat up or expel gas within the galaxy, making it difficult for the gas to cool and condense into new stars. These powerful outflows, jets, and winds can drive enormous amounts of gas out of the galaxy's central regions, effectively quenching star formation. This process can lead to the cessation of star formation in the entire galaxy, transforming it from a star-forming, often spiral galaxy into a more quiescent, elliptical galaxy. However, in some scenarios, AGN activity can enhance star formation. The outflows and jets from the AGN can compress gas clouds as they travel through the interstellar medium, triggering the collapse of these clouds into stars. This is a more localized effect and tends to happen in regions where the AGN-induced pressure is just right to promote cloud collapse without dispersing the gas completely. This dual nature of AGN feedback illustrates the complex interplay between the central black hole and its host galaxy. AGNs also have a profound impact on the larger scale structure of their host galaxies and beyond. The energy released by an AGN can help regulate the growth of the host galaxy by controlling the availability of star-forming material. This regulatory effect extends to the galactic halo, influencing the temperature and density of gas within the galaxy's gravitational influence. Additionally, AGNs can affect the intergalactic medium, enriching it with heavy elements through the expulsion of gas and dust, thereby influencing the evolution of neighboring galaxies and the broader cosmic environment. Observationally, active galactic nuclei contribute to the distinct properties seen in various galaxy types, such as Seyfert galaxies, quasars, and blazars. Each of these galaxy types provides unique insights into the life cycle and characteristics of AGNs, allowing astronomers to further unravel the mysteries of these dynamic cosmic phenomena. The study of AGNs not only helps us understand the mechanics of galaxies, but also offers a glimpse into the profound forces shaping the universe itself. Astronomers are continuously unlocking the secrets of our universe, and understanding active galactic nuclei, AGN has become a pivotal piece of the cosmic puzzle. These mysterious regions of intense energy centered around supermassive black holes not only intrigue scientists, but also offer a rare window into the distant past. Some of the most luminous AGNs, known as quasars, can be seen at incredibly vast distances, acting as beacons that shine a light on the early stages of the universe. They provide invaluable clues about the conditions and processes that shaped galaxies in their infancy, offering a glimpse into the birth of galaxies and their subsequent development. AGN are also much more than just fascinating celestial objects. They play a significant role in shaping the very galaxies that host them. Through complex feedback mechanisms, these supermassive black holes influence their host galaxies in profound ways. Their energy output can either inhibit or stimulate star formation, dramatically altering galactic structures and even affecting the interstellar and intergalactic media. These interactions underscore the crucial role that AGN and their central black holes play in galaxy evolution. As we continue to study these phenomena, it becomes clear that AGNs are not merely isolated objects, but rather central players in our broader understanding of the cosmos. However, the mysteries don't stop with AGNs. One of the most intriguing cosmic phenomena currently puzzling astronomers are our ultra-diffuse galaxies, UDGs. These ghostly, faint galaxies are as large as the Milky Way, but contain far fewer stars. Their sparse stellar populations make them appear almost invisible, yet they are anything but ordinary. What truly sets UDGs apart is their remarkable content of dark matter. Despite their low star counts, UDGs are dominated by dark matter, which constitutes the majority of their mass. This bizarre characteristic raises numerous questions about the formation and structure of these galaxies. challenging our conventional understanding of how galaxies form and evolve. One of the key questions surrounding UDGs is how they come into existence. Traditional theories of galaxy formation suggest that galaxies form through the accretion of gas followed by the formation of stars, all regulated by the gravitational influence of dark matter halos. But UDGs defy this simple model. Unlike other galaxies, UDGs show little to no star formation, leaving scientists to question why they behave so differently. Several hypotheses have been put forward to explain their peculiarities. One theory suggests that UDGs may be failed galaxies. These galaxies, with their massive dark matter halos, failed to convert gas into stars efficiently. This inefficiency could be the result of early feedback processes, such as the winds from supernovae or the powerful outflows of active galactic nuclei, which expelled the gas before it had the chance to form stars. Alternatively, UDGs may have formed through tidal interactions with larger galaxies or galaxy clusters. These interactions, which often strip away stars and gas, could explain the sparse star populations in UDGs. Regardless of their origin, the role of dark matter in UDGs remains one of the most profound mysteries in modern astronomy. Observations suggest that UDGs are exceptionally rich in dark matter, raising questions about the very nature and distribution of this elusive substance within galaxies. Some UDGs, such as those found in the Coma cluster, seem to possess dark matter halos with masses comparable to those of much larger galaxies, yet their star counts remain low. This discrepancy hints at a deeper relationship between dark matter and galaxy formation, one that is still not fully understood. The discovery of UDGs has forced astronomers to rethink existing models of cosmology. Standard cosmological models, which predict certain distributions and behaviors of galaxies based on the interactions between dark matter and baryonic matter, struggle to explain the unusual properties of UDGs. Their discovery challenges these models, prompting researchers to explore new theories that may account for these enigmatic galaxies. With each new observation and theory, the mysteries surrounding UDGs and AGNs continue to deepen, driving forward our understanding of the cosmos and its formation. These celestial oddities may just hold the key to unlocking some of the universe's most profound secrets. For instance, some theories suggest that ultra-diffuse galaxies, UDGs, could form in dark matter halos with unique properties that are still being fully characterized, revealing exciting new possibilities in the realm of dark matter physics. The very existence of UDGs in a wide range of environments, from densely packed galaxy clusters like Coma to more isolated regions, adds a layer of complexity that challenges traditional models of galaxy formation. In clusters, UDGs might be the remnants of tidal interactions, but in isolation, other processes could be at play. The contrasting formation mechanisms across different environments highlight the need for comparative studies to disentangle the multiple factors that contribute to the diverse characteristics of these galaxies. Furthermore, the composition and stability of UDGs are points of major intrigue. These galaxies often have minimal stellar mass, yet a significant presence of dark matter, raising important questions about their internal dynamics and long-term stability. How do these diffuse systems maintain their structure, resisting the tidal forces that would normally tear apart less stable systems? This is a compelling area of study, as understanding how UDGs preserve their shape in the vast, harsh expanses of space could provide essential insights into the nature of cosmic structures and their resilience over time. The mystery surrounding UDGs invites astronomers to refine existing models and develop new theories that account for their unusual formation processes and the interplay of dark matter and ordinary matter within these ghostly galactic bodies. Moreover, ring galaxies, among the most visually stunning and distinctive structures in the universe, offer a different set of fascinating insights. Characterized by a bright, luminous ring of stars and other material surrounding a typically dimmer core, these cosmic structures are thought to form primarily due to galactic collisions. Their study offers an extraordinary opportunity to explore the dynamics of colossal cosmic events and the evolution of galaxies. The most widely accepted theory for the formation of ring galaxies centers around what is called a bullseye collision. In such an event, a smaller, intruding galaxy passes directly through the center of a larger disk galaxy. This dramatic interaction triggers a shockwave that travels outward through the disk, compressing gas and dust. The compression triggers a burst of star formation, which manifests as a bright ring surrounding the galaxy's core. Gravitational forces during these collisions are immense, leading to the radial displacement and restructuring of material into the ring shape we observe. A prime example of a ring galaxy is the Cartwheel Galaxy, located about 500 million light-years away in the constellation Sculptor. Studying such a galaxy provides astronomers with a natural laboratory to observe the effects of shockwaves and gravitational forces on galactic evolution. The bright ring in these galaxies is typically rich in young, hot stars, indicative of recent and intense star-forming activity, while the core may feature older stars, with star formation less pronounced or entirely disrupted due to the collision. Ring galaxies offer significant insights into the dynamics of galactic collisions. They reveal how such events can reshape entire galaxies and lead to the formation of new structures. Although the occurrence of perfect bullseye collisions is rare, when they do happen, they offer a fascinating demonstration of angular momentum conservation and the propagation of density waves through the galactic disk. Furthermore, studying ring galaxies helps astronomers understand the distribution and behavior of interstellar material within galaxies. The shockwave from the collision provides a glimpse into the gas density and the conditions necessary for star formation. By examining the color, luminosity, and distribution of stars within the ring, researchers can determine the age of the starburst, which helps piece together a timeline for the dynamic interactions and evolutionary processes that shape galaxies over billions of years. Additionally, the exploration of ring galaxies and their formation plays a crucial role in advancing our knowledge of galaxy formation and evolution. These captivating phenomena underscore the significance of minor mergers, collisions between galaxies of vastly different sizes that are key in shaping the structure and star formation rates of galaxies in our universe. These cosmic interactions, often perceived as destructive, have an unexpected outcome. They can breathe new life into galaxies by supplying fresh gas, which fuels subsequent rounds of star formation. Ring galaxies, the stunning byproducts of such galactic collisions, offer us a front-row seat to the chaos and beauty of the universe. These ring-shaped structures are the result of head-on collisions between galaxies, where shockwaves ripple through the galactic disks, rearranging stars, gas, and dust in a spectacular display. By studying these galaxies, astronomers gain profound insights into the dynamics of galactic interactions, the distribution and behavior of interstellar matter, and the processes that spark star formation. In essence, ring galaxies serve as a cosmic laboratory where the story of galactic evolution is written in the stars and the rings that encircle them. These extraordinary structures allow us to decipher the intricate narrative of galaxy life cycles, adding depth to our understanding of the vast cosmic tapestry in which we exist. Equally intriguing are the elusive dark galaxies, an astonishing discovery that offers a glimpse into the unseen realms of our universe. These mysterious entities, composed almost entirely of dark matter, are notably absent of the luminous stars that illuminate typical galaxies. Without these stars to shine a light on them, dark galaxies remain invisible to our telescopes, revealing their existence only through their gravitational influence on nearby visible matter or through subtle distortions in the cosmic microwave background radiation. Imagine, if you will, entire galaxies, vast, sprawling, and silent, gliding through the cosmos, undetectable by our instruments, yet intricately woven into the very fabric of the universe. The implications of dark galaxies are profound. They reinforce our understanding of dark matter, a substance that makes up approximately 27% of the universe. This elusive force, 5 times more abundant than ordinary matter, exerts a gravitational pull yet emits no light. The discovery of dark galaxies, composed solely of dark matter, suggests that this invisible entity plays a far more complex and pivotal role in galactic formation and evolution than we once thought. Beyond this, dark galaxies could serve as cosmic laboratories, providing scientists with the rare opportunity to study dark matter in isolation from the baryonic matter that typically accompanies galaxies. Such investigations could lead to groundbreaking insights into new physics, potentially reshaping our understanding of the fundamental building blocks of the universe. While dark galaxies remain enigmatic, their discovery propels us toward a deeper investigation into the cosmic puzzle of dark matter. These hidden giants may hold the key to unlocking secrets that could redefine our understanding of the universe's origins and structure. Galaxy clusters, on the other hand, represent some of the largest and most awe-inspiring structures in the cosmos. These immense gravitational behemoths bind together hundreds, if not thousands, of galaxies, creating gravitational wells that reveal the complex architecture of the universe. Imagine, instead of perceiving galaxies as isolated islands, viewing them as interconnected nodes within a vast cosmic network. This cosmic web is an intricate framework stretching across billions of light years, with galaxy clusters acting as the glowing hubs where filaments of dark matter and gas converge. The study of galaxy clusters through various observational methods offers an unparalleled window into the large-scale structure of the universe. One of the key techniques used is gravitational lensing, where the immense mass of a galaxy cluster bends and magnifies the light from more distant objects behind it. This phenomenon not only maps the visible matter within the cluster, but also traces the distribution of dark matter, an invisible yet dominant force that makes up the bulk of the cluster's mass. Through gravitational lensing and other techniques, galaxy clusters serve as cosmic beacons, illuminating the structure of the universe and revealing the fundamental forces at play in its evolution. Additional X-ray observations of the hot gas within galaxy clusters, which can soar to temperatures reaching tens of millions of degrees, offer profound insights into the workings of these colossal cosmic structures. The X-rays emitted by this hot gas highlight the intracluster medium, revealing dynamic processes such as collisions, mergers, and the interaction of galaxies that shape these massive assemblies of stars, gas, and dark matter. As cosmologists study the spatial distribution and evolution of galaxy clusters, they unlock clues about the properties of dark matter and dark energy, two enigmatic forces that govern the cosmos. Dark energy, in particular, is believed to drive the accelerated expansion of the universe, playing a pivotal role in the universe's destiny. Through this lens, galaxy clusters emerge not just as stellar formations, but as both signposts and laboratories that enhance our understanding of the universe's grand architecture and the fundamental laws that govern it. Moreover, gravitational lensing, often described as a cosmic magnifying glass, offers astronomers a powerful tool to peer deeper into the universe. When a massive object, such as a galaxy or galaxy cluster, sits between a distant light source and the observer, its gravitational pull bends and focuses the light, creating fascinating distortions in the sky. These include multiple images of a single distant galaxy, arcs of light, and even rings, known as Einstein rings. Through meticulous analysis of these distortions, scientists can map out the presence and concentration of dark matter, which, unlike ordinary matter, does not emit light and remains invisible. Gravitational lensing thus allows us to see the otherwise hidden structures of the universe. The insights gained through gravitational lensing reveal a remarkable truth about dark matter. It does not spread uniformly across galaxies. Instead, it tends to clump together, forming dense cores and extended halos around visible matter. This clumping pattern aligns with current cosmological models and simulations, suggesting that dark matter plays an essential role in shaping the formation and structure of galaxies. Detailed studies of lensing phenomena have uncovered that many galaxies contain significantly more dark matter than visible matter, sometimes by a ratio as high as 10:1. These dark matter halos extend far beyond the visible parts of galaxies, often encompassing them in a vast, unseen web of gravitational influence. Additionally, gravitational lensing allows scientists to investigate smaller-scale features within the dark matter halos, features that are typically beyond the reach of traditional observational techniques. These small-scale structures may provide vital clues about the nature of dark matter particles and their elusive interactions, helping scientists refine their understanding of this mysterious substance. Through such sophisticated cosmic-scale experiments, gravitational lensing not only reveals the hidden architecture of dark matter, but also enhances our models of how galaxies and the universe itself have evolved over billions of years. In this way, lensing acts as a window into both the large-scale structures and the fundamental nature of the universe. Dwarf galaxies, although tiny when compared to their massive counterparts, play a crucial role in shaping the evolution of larger galaxies. These small galaxies are abundant across the universe and often act as cosmic building blocks. Dwarf galaxies are often the primary reservoirs of dark matter and gas, and through a process known as hierarchical merging, they frequently collide and merge with larger galaxies, contributing stars, gas, and dark matter to the larger galactic structures. This ongoing merger process profoundly influences the shape and development of massive galaxies, including our very own Milky Way. When dwarf galaxies are absorbed into a larger host galaxy, they can trigger intense bursts of star formation. This influx of fresh gas invigorates the older stellar populations of the host galaxy, leading to the formation of new star clusters, and, in some cases, even the development of new spiral arms. These interactions can also induce dynamic changes in the galaxy's structure, influencing its disk thickness, the formation of bars, and the overall spiral configuration. The resulting stellar streams and tidal tails are visible remnants of these cosmic cannibalistic events, leaving behind observable evidence that can be traced back to the merger event. Examining the chemical composition of stars in galaxies affected by these mergers provides astronomers with a deeper understanding of the chemical evolution and enrichment history of larger galaxies. This analysis sheds light on how the elements essential for life were distributed throughout the cosmos over time, revealing the intricate process by which stars, gas, and dark matter mix and evolve in cosmic environments. The discovery and study of dwarf galaxies surrounding the Milky Way, including the enigmatic Sagittarius dwarf elliptical galaxy and the Large Magellanic Cloud, highlight the profound and lasting impact these small galaxies have on the larger scale structure of the universe. By gradually building up mass, triggering bursts of star formation, and altering the dynamics of their larger neighbors, these small galaxies are essential to the ongoing evolution of our cosmic neighborhood. Dwarf galaxies offer an extraordinary glimpse into the complex and dynamic forces shaping the universe, revealing a deep, intricate relationship between cosmic structures at various scales. The interactions between the intergalactic medium, IgM, and the cosmic web stand as fundamental components of this cosmic ballet, sculpting the very fabric of space and the evolution of galaxies. The IgM, an expansive, diffuse sea of gas predominantly composed of hydrogen and helium, fills the vast voids between galaxies. But this is no random arrangement. This gaseous medium follows a well-defined structure, aligning itself with the vast filaments, sheets, and voids that make up the cosmic web, a monumental network that spans the entire universe. These filaments within the cosmic web serve as the arteries through which matter flows, driven by the powerful gravitational forces of dark matter. The intersections of these filaments act as the crucibles of galaxy formation, where galaxies tend to congregate and form clusters, concentrated in the nodes of this web. As matter funnels into these regions, the IgM, heated to millions of degrees, radiates X-rays, signals of the immense energy at play. This process, known as accretion, is essential to the growth and evolution of galaxies. It provides the vital gas needed for star formation and fuels the voracious appetites of supermassive black holes, which consume the gas at the centers of many galaxies. Beyond merely being a conduit for galactic material, the IgM plays a pivotal role in the chemical enrichment of the universe. As galaxies evolve and produce stars, they expel elements back into the IgM through supernova explosions and stellar winds. These events scatter heavier elements like carbon, oxygen, and iron into the surrounding gas, enriching the intergalactic medium and facilitating the formation of new stars and planets. This ongoing interaction between galaxies and the IgM not only shapes the chemical makeup of the universe, but also reveals much about the early stages of cosmic evolution. Through quasar absorption lines, where the light from distant quasars is filtered through the IgM, scientists are able to probe the state and distribution of matter in the early universe, offering a window into the very origins of the cosmos. In essence, the IgM and the cosmic web are not passive bystanders in the grand cosmic story. They are active players orchestrating the flow of matter and energy. These structures foster the creation and evolution of galaxies, propelling the universe's development and enriching it with the very elements that form stars, planets, and life as we know it. In the same vein, galactic halos present a profound challenge to our understanding of galaxy formation. These vast, spherical regions of dark matter envelop galaxies, extending far beyond their visible stellar components. Unlike the concentrated disks and bulges that define galaxies, these halos are diffuse, yet they contain a significant portion of a galaxy's total mass. Their invisible nature, unlike the shining stars and gas of galaxies, makes them incredibly difficult to detect. Yet, despite their elusiveness, dark matter halos reveal their presence through their gravitational influence, particularly in the form of galaxy rotation curves and gravitational lensing. This discovery of dark matter halos has had a transformative impact on our models of galaxy formation. Traditional models, which only considered visible matter, struggled to explain why galaxies rotate the way they do, faster than expected in their outer regions. Dark matter halos provide the crucial missing piece to this puzzle, offering an explanation for the anomalous rotation speeds by accounting for the unseen mass that surrounds galaxies. However, the true nature of dark matter itself remains one of the universe's greatest mysteries. Candidates such as weakly interacting massive particles, WIMPs, and axions have been proposed, but none have yet been directly detected, leaving a critical gap in our comprehensive understanding of the cosmos. Moreover, galactic halos present challenges to our comprehension of galaxy evolution. The interaction between dark matter and the visible matter within these halos plays a crucial role in various processes, including star formation and galactic mergers. For instance, the stable and enduring nature of dark matter halos provides a gravitational scaffold, allowing gas to cool and condense, creating the conditions necessary for new stars to form. Over billions of years, this interaction governs the life cycle of galaxies, from their birth to their eventual evolution into complex, massive systems. Ultimately, the study of dwarf galaxies, the IGM, the cosmic web, and dark matter halos paints a picture of a universe that is far from static. These structures interact with one another in a complex, delicate balance, driving the growth, transformation, and enrichment of galaxies and the universe at large. Each discovery brings us closer to understanding the forces that shape the cosmos, opening new avenues of exploration that promise to reveal even more about the vast, mysterious universe we inhabit. The structure and substructure of halos, including the presence of subhalos, smaller concentrations of dark matter within the larger halos, significantly impact the dynamics and eventual fate of satellite galaxies. By studying these halos, we can gain profound insights into the hierarchical nature of galaxy assembly and the critical role that dark matter plays in shaping the universe. Galactic halos present unique challenges to our current models, but they also provide an essential framework for understanding the cosmic web and the intricate dance of galaxies within it. A key feature in this cosmic understanding is the Great Attractor, one of the most enigmatic and powerful forces in our universe. This gravitational anomaly exerts an immense pull that affects entire clusters of galaxies, including our very own Milky Way. Positioned approximately 150 to 200 million light-years away in the direction of the Centaurus constellation, the Great Attractor is shrouded in mystery. Its exact nature remains elusive due to its position behind the dense plane of the Milky Way, a region astronomers refer to as the zone of avoidance. This zone makes it difficult to observe the Great Attractor directly, yet its gravitational influence is undeniable. Several hypotheses attempt to explain the Great Attractor's origins. One of the leading theories posits that it is a supercluster, or even a complex of superclusters, that aggregates vast amounts of mass, including both visible galaxies and an enormous amount of dark matter. Observations have shown that the area around the Great Attractor is densely packed with galaxy clusters, such as the Norma cluster, which contribute to its powerful gravitational pull. Dark matter, as is typical with large-scale cosmic structures, plays a vital role in shaping this gravitational anomaly. Furthermore, the Laniakea supercluster, which includes our Milky Way, is believed to be part of a larger structure that funnels toward the Great Attractor. This illustrates the interconnected nature of cosmic flows and gravitational dynamics, with galaxies in our vicinity being drawn into its immense gravitational well. However, recent observations suggest that even greater cosmic structures exist beyond the Great Attractor. The Shapley supercluster, located approximately 650 million light-years away, might be a larger entity that influences the gravitational dynamics we observe. This raises the intriguing possibility that what we perceive as the Great Attractor could merely be an intermediate feature in a much grander cosmic structure, part of an expansive network of superclusters. Understanding the Great Attractor opens up a host of questions about the distribution of mass in the universe and the role of dark energy in cosmic expansion. As astronomers continue to refine their tools for observing distant regions of the universe, we may soon gain a clearer picture of the true nature of the Great Attractor. This deeper insight could unlock a new understanding of the invisible forces that sculpt the cosmos, shedding light on how vast structures like this influence the behavior and fate of galaxies. In a seemingly unrelated but equally profound mystery, the WOW signal remains one of the most compelling enigmas in the search for extraterrestrial intelligence. Detected on August 15, 1977, by Dr. Jerry Amon using the Big Ear radio telescope at Ohio State University, this narrowband radio signal was unlike anything previously recorded. The signal stood out due to its unusual intensity and frequency, lasting a brief 72 seconds. When Amon first reviewed the data, he was so struck by the anomaly that he scribbled "WOW" in the margins of the printout, a label that has since become synonymous with the signal itself. Despite numerous attempts to locate the signal again, the WOW signal has never been detected a second time. Its peculiar characteristics have sparked widespread debate about the possibility of it being an extraterrestrial transmission. While some have suggested natural explanations, the signal's intense and unique properties continue to fuel questions about the existence of intelligent life beyond Earth. The WOW signal remains an enduring mystery, a tantalizing hint that perhaps we are not alone in the vast reaches of space. The search for answers continues, with each new attempt to decode the signal bringing us closer to understanding whether it was truly a message from another civilization or just a fleeting anomaly of the cosmos. The WOW signal challenges our understanding of the universe in profound and unsettling ways. This enigmatic signal, detected in 1977, carries with it a mystery that has perplexed scientists for decades. Its narrowband nature, a distinctive feature, sets it apart from the usual cosmic noise that we encounter. Most natural cosmic phenomena produce broadband noise, but the WOW signal exhibited a sharp, focused frequency, precisely what researchers in the search for extraterrestrial intelligence, SETI, would expect from an artificial source. If this signal did indeed originate from an intelligent civilization, it would imply that such a civilization possesses technology far more advanced than ours, capable of transmitting powerful radio waves across interstellar distances. However, the key challenge is its single occurrence. The WOW signal's lack of repetition makes it nearly impossible to decode or interpret definitively. Scientists remain in a state of tantalizing uncertainty, unable to say with certainty whether the signal was a fluke, a natural anomaly, or the first communication from an extraterrestrial intelligence. This ambiguity pushes the boundaries of human curiosity and scientific rigor, inviting more questions than answers. It serves as a reminder of how much we still have to learn about the cosmos and our place within it. This enigmatic signal joins a growing list of cosmic anomalies that continue to provoke debate and challenge our assumptions. One of the most recent and intriguing discoveries is that of fast radio bursts, FRBs. While many of these bursts are believed to have natural astrophysical origins, their initial discovery sparked speculation about possible artificial sources. These intense, fleeting bursts of energy raise critical questions for the SETI community, urging them to reconsider and refine their detection strategies. They must balance the search for natural explanations with the openness to extraordinary possibilities, all the while questioning whether our current technology and observational limitations might be preventing us from recognizing extraterrestrial communications. As our detection tools become more advanced, these unexplained signals continue to spark our imagination. They propel us forward in our quest to answer one of humanity's most profound questions. Are we alone in the universe? This search is more than just a scientific endeavor. It touches on something deeper, our collective desire to understand the unknown and connect with something beyond ourselves. Among the many cosmic mysteries, Tabby's star, formerly known as KIC 8462852, stands out as one of the most perplexing and captivating. Discovered by the Kepler Space Telescope and named after astronomer Tabitha Boyajian, this star has confounded scientists with its highly irregular dimming patterns. Unlike typical exoplanet transits, where the dimming of a star's light occurs in a predictable, regular pattern, Tabby's star exhibits erratic and unpredictable dips in brightness. These fluctuations can reach as much as 22%, far beyond the usual range seen in exoplanetary systems. This extraordinary behavior has led to numerous hypotheses, with no clear answers in sight. Several natural explanations have been proposed for the strange dimming patterns. One of the most widely discussed theories suggests that the star is periodically obscured by a large cloud of disintegrating comets or debris from a shattered planet. While this scenario seems plausible, it would require an immense and highly improbable concentration of material to explain the magnitude and irregularity of the dimming. Another possibility involves intrinsic stellar variability, meaning that the star itself may be undergoing changes that affect its brightness. However, this idea too faces significant challenges in both observation and theory. The mystery deepens when considering more speculative hypotheses. Some astronomers have suggested the presence of an enormous, ringed, or oddly shaped exoplanet, which could explain the irregular dimming. However, this theory also faces numerous obstacles, including the difficulty of detecting such an object with current technology. As the mystery of Tabby's star has captured the public's imagination, it has also led to the discovery of other stars exhibiting similar unexplained dimming patterns. One such star, VVVT08, observed by the VISTA variables in the Via Lactea survey, also shows drastic reductions in brightness. This has led scientists to consider a range of potential causes, including large disk structures or even previously unknown types of stellar companions. Among the most fascinating, albeit speculative ideas is the possibility of megastructures built by an advanced extraterrestrial civilization. Some have proposed that a Dyson sphere, a vast, energy-harvesting structure surrounding a star, could be responsible for the mysterious dimming. While there is no concrete evidence to support this hypothesis, the concept of alien megastructures captures the imagination of both the scientific community and the public alike. It serves as a reminder of the importance of keeping an open mind in scientific inquiry, embracing the possibility of extraordinary phenomena, even in the face of uncertainty. As we continue to explore the cosmos and search for answers to these mysteries, we are reminded that the universe is vast, and we are only beginning to scratch the surface of what might lie beyond our current understanding. Whether the WOW signal, Tabby's star, or other cosmic anomalies represent signals from distant civilizations or the natural workings of the universe, they all challenge us to expand our view of reality and continue the search for life beyond Earth. The mysteries of the universe continue to beckon, with cutting-edge research pushing the boundaries of our understanding. With each leap in technology, astronomers are gaining deeper insights into some of the cosmos' most enigmatic phenomena, particularly the stars that appear to flicker and dim in ways that defy explanation. As technology evolves, harnessing data from an ever-growing array of telescopes and astronomical surveys, the tools we have at our disposal are becoming more sophisticated, enabling us to capture higher resolution images and conduct more detailed analyses. These advancements promise to illuminate the true nature of these celestial bodies. Are their fluctuating light patterns the result of natural phenomena? Or do they hint at something far more exotic, something beyond our current comprehension? One thing is certain, they fuel our curiosity and serve as a catalyst for deeper exploration into the profound mysteries of our universe. This pursuit is not limited to stars alone. Vast, seemingly empty regions of space known as cosmic voids also present a unique and intriguing challenge. These enormous voids, spanning tens to hundreds of millions of light years, are interspersed throughout the universe's grand cosmic web. The web is a vast network of interconnected filaments that hosts galaxies and clusters of galaxies. Within these cosmic voids, Galaxies are sparsely scattered, and matter is less densely packed compared to the denser, more clustered regions of space. This voided environment offers cosmologists a rare glimpse into the fundamental workings of the universe, with profound implications for our understanding of dark matter and dark energy. The challenges posed by cosmic voids are vast. As the universe continues to expand under the influence of dark energy, these vast voids offer a unique testing ground. Unlike denser regions where gravitational interactions and clustering dominate, voids are more sensitive to the universe's expansion. This makes them an excellent natural laboratory for testing cosmological theories. As we delve deeper into these regions, we begin to uncover more about the nature of dark energy, as well as explore alternative theories of gravity. How galaxies evolve within these voids and how they interact with one another could offer tantalizing clues that push the boundaries of our current cosmological paradigm. One of the more surprising discoveries is how galaxies within cosmic voids differ dramatically from those in more densely packed environments. These void galaxies exhibit lower luminosities, reduced star formation rates, and unusual shapes. This divergence suggests that environmental factors play a crucial role in shaping the evolution of galaxies. By studying void galaxies in detail, astronomers can isolate these environmental influences, helping to unravel the intrinsic processes that govern galaxy formation and growth. However, integrating these observations into larger-scale cosmological models proves difficult. The standard model of cosmology, known as the lambda cold dark matter, LILCDM model, has been successful in explaining many of the universe's large-scale features. Yet, discrepancies arise when we examine the small-scale structure of voids, particularly in the distribution and properties of galaxies within them. These discrepancies indicate that our current models may be incomplete, forcing scientists to refine and enhance their simulations. They must now account for more complex interactions between dark matter, dark energy, and ordinary matter. The study of cosmic voids is not only helping to identify gaps in our models, but also offering an opportunity to calibrate and adjust our understanding of the universe. As we gather more data, the significance of cosmic voids grows. These enigmatic regions challenge the very foundation of our cosmological models, serving as both a puzzle and a mirror that reflects the gaps in our understanding. The ongoing study of voids, fueled by more advanced observational tools, could unlock revolutionary insights into the universe's structure, evolution, and the fundamental forces that govern it. In addition to voids, another fascinating anomaly has captured the attention of astronomers: the cosmic microwave background, CMB, cold spot. This region in the CMB, an afterglow of the Big Bang, exhibits a temperature significantly lower than the surrounding areas, an anomaly that has perplexed scientists for years. Discovered by the Wilkinson Microwave Anisotropy Probe, WMAP, and later confirmed by the Planck satellite, the CMB cold spot spans about 20 degrees and is approximately 70 microkelvins colder than the average temperature of the CMB, which is around 2.7 Kelvin. The CMB provides a snapshot of the early universe, roughly 380,000 years after the Big Bang, offering crucial insights into the formation of large-scale structures in the cosmos. Variations in its temperature and density are expected, yet the cold spot's unexplained nature continues to challenge our models of cosmology, leaving open the tantalizing possibility of something even more profound lurking in the fabric of space-time. As technology continues to advance, future studies hold the promise of shedding more light on these cosmic enigmas. Whether these phenomena are the result of previously unknown natural processes or whether they suggest the existence of entirely new physics remains to be seen. Yet, one thing is certain: our universe is far more complex and mysterious than we could have ever imagined. Each discovery opens the door to new questions, propelling us deeper into the uncharted territories of the cosmos. However, the CMB cold spot stands out as an anomaly that deeply challenges our current understanding of cosmology. This peculiar phenomenon has become a focal point in scientific discussions, offering the potential to reshape or even redefine the standard model of the universe. One of the most significant implications of the CMB cold spot is its ability to test and refine our existing theories about the cosmos. Most conventional explanations suggest that this cold spot is caused by a supervoid, a massive, underdense region of the universe lying along our line of sight. Such voids are thought to cause the integrated Sachs-Wolf effect, where photons lose energy as they travel through the void, resulting in a cooler region in the cosmic microwave background, CMB. Despite the seeming plausibility of this theory, it fails to account for the extreme size and intensity of the cold spot, leaving the door open for alternative, more exotic explanations. One such theory is the possibility that the CMB cold spot might actually be evidence of a parallel universe. The multiverse hypothesis proposes that our universe is just one of many, each potentially governed by different physical laws and constants. If this theory holds any weight, the cold spot could be the lingering aftermath of a collision between our universe and another one. The cold spot would then represent a bruise left by this cosmic impact, an intriguing and yet unproven hypothesis that stirs the imagination of both scientists and philosophers alike. Though highly speculative and lacking direct evidence, this theory ignites discussions about the very fabric of reality and the potential existence of parallel universes. To test these theories, scientists are continuing to scrutinize the CMB cold spot through ongoing and future observations. This includes detailed studies of surrounding cosmic structures, galaxy distributions, and extensive computer simulations. With the advancement of observational technology, we may one day get closer to solving this cosmic riddle. Whether the cold spot is a mere statistical anomaly, the result of large-scale cosmic structures, or a clue pointing towards something far more extraordinary, it continues to captivate the imagination of scientists, pushing the boundaries of our understanding of the universe. Fast radio bursts are another mysterious and perplexing phenomenon that has captured the curiosity of astronomers since their discovery in 2007. These extraordinarily brief but intensely powerful bursts of radio waves last only a few milliseconds, yet in that brief moment, they emit more energy than our sun does in an entire day. Despite numerous detections over the years, the precise origins and mechanisms behind FRBs remain elusive, making them one of the most fascinating enigmas in modern astronomy. One of the primary mysteries surrounding FRBs is the unknown source of these bursts. Theories range from highly magnetic neutron stars, known as Magnetars, to the activity of black holes, to more speculative ideas, such as the possibility that they are signals from extraterrestrial civilizations. The existence of repeating FRBs, those that emanate from the same location repeatedly, adds yet another layer of complexity. For instance, the well-known repeater FRB 111102 has shown erratic burst patterns that challenge simple explanations. The fact that some FRBs repeat while others appear as one-off events suggests that multiple mechanisms or progenitors could be responsible for producing these bursts, further complicating our efforts to unravel their origin. Both the CMB cold spot and FRBs serve as powerful reminders of how much we still have to learn about the universe. They represent the frontiers of cosmological research, constantly challenging our assumptions and encouraging us to push the boundaries of our scientific knowledge. Whether they will ultimately lead to groundbreaking discoveries or remain elusive puzzles, these phenomena will continue to ignite the quest for understanding, pushing the limits of what we know about the cosmos. The study of fast radio bursts, FRBs, has become one of the most captivating and perplexing areas of modern astronomy. These enigmatic phenomena, often originating billions of light years away, are a constant reminder of the immense power lurking within the universe. Their distances suggest that whatever is producing these bursts must be capable of generating unimaginable amounts of energy, far surpassing anything humanity has ever produced. What truly heightens the intrigue surrounding FRBs, however, is their dispersion measure, a critical piece of data that quantifies the amount of interstellar and intergalactic material that the signal has passed through. This measure provides further evidence that FRBs have extragalactic origins, distances so vast that understanding the environments in which they originate becomes a monumental challenge. The challenge, however, doesn't end with the FRB's origins. Their vast distance complicates any attempt to precisely pinpoint their exact locations, leaving scientists to search through immense regions of space for potential clues. Over time, some FRBs have been traced to specific galaxies, and even particular regions within those galaxies, offering some insight. But as with any frontier of science, each discovery raises as many questions as it answers, further underscoring the complexities of these cosmic events. Despite these challenges, the pace of discovery is accelerating thanks to advanced radio telescopes like CHIME in Canada and ASCAP in Australia. These cutting-edge instruments are allowing for more frequent and more precise detections of FRBs, gradually improving our ability to track their origins. Nevertheless, each new detection often brings more complexity. The rapid transient nature of FRBs, combined with their enormous energy output, means that understanding them in full remains an ongoing challenge. They continue to defy our understanding of the most extreme environments in the universe, pushing the limits of what we know about astrophysical processes. As observational techniques improve, scientists are optimistic that we may soon be able to unlock the mystery behind these phenomena. With every new breakthrough, we inch closer to unveiling the secrets of these powerful cosmic events, potentially opening up new realms of astrophysical knowledge. At the same time, the universe has other elusive mysteries waiting to be understood. Ultra-high energy cosmic rays, UHCRs, stand as one of the most energetic and enigmatic phenomena ever observed. These charged particles possess energies that surpass 10 to 18 electron volts light, making them millions of times more energetic than anything produced in particle accelerators on Earth. This extreme energy presents a problem for scientists. The sources of these cosmic rays remain largely unknown, despite decades of research. Various theories have been proposed, but no conclusive evidence has emerged to pinpoint their origins. A leading hypothesis suggests that UHCRs may originate from extragalactic sources, particularly active galactic nuclei, AGNs. AGNs are the powerful cores of galaxies, typically powered by supermassive black holes. These black holes are capable of generating tremendous energy by accreting matter. As the material spirals into the black hole, it emits jets of energy that can extend millions of light years into space. These jets, filled with intense magnetic fields and energetic particles, may accelerate cosmic rays to ultra-high energies. The extreme conditions in these regions provide the perfect environment for UHCRs to be born. Another intriguing source for UHCRs is gamma-ray bursts, GRBs. These violent explosions, often observed in distant galaxies, are associated with the collapse of massive stars or the merger of neutron stars. GRBs are known to release enormous amounts of energy, and the relativistic jets produced during these events could accelerate particles to speeds sufficient to reach ultra-high energies. However, the unpredictable nature of GRBs, which are sporadic and transient, makes it difficult to directly link them to UHCRs. Additionally, some theories suggest that magnetars, which are neutron stars with extraordinarily strong magnetic fields, could be responsible for generating UHCRs. Magnetars are known to emit intense bursts of energy, and through processes such as magnetic reconnection and relativistic shocks, they might accelerate cosmic rays to these extreme energies. One of the more compelling aspects of UHCRs is their isotropic distribution, meaning they arrive uniformly from all directions in the sky. This feature supports the notion that UHCRs may primarily originate from sources outside our galaxy. Should this hypothesis prove true, it would provide a fascinating glimpse into the workings of distant high-energy astrophysical phenomena. But as with FRBs, the exact origins of UHCRs remain elusive, and further breakthroughs in observational techniques and technology are essential for piecing together this cosmic puzzle. The mystery of both FRBs and UHCRs stands as one of the greatest challenges of modern astrophysics. While scientists are making significant strides in unraveling the origins of these phenomena, much remains to be understood. As new data and technologies emerge, the universe's most extreme environments may soon reveal their deepest secrets, changing the way we view the cosmos forever. We would expect a more anisotropic distribution due to the Milky Way's structure, but recent observations have shown some degree of anisotropy, suggesting that specific extragalactic sources might contribute significantly. However, this idea remains speculative and requires further evidence before we can make any definitive conclusions. One of the more intriguing elements of this puzzle involves the so-called GZK cutoff, named after the physicists Greisen, Zatsepin, and Kuzmin. This theoretical limit suggests that cosmic rays with energies above approximately 6 quintillion electron volts, 6 × 10^10 EVs, should interact with cosmic microwave background be photons losing energy over long distances. Yet, recent observations have revealed cosmic rays with energies that surpass this theoretical limit, challenging our understanding of high-energy astrophysics and suggesting the possible existence of nearby or particularly powerful sources. The sources of ultra-high-energy cosmic rays, UHECRs, remain one of the most significant mysteries in astrophysics. Are they coming from active galactic nuclei, AGNs, gamma-ray bursts, GRBs, Magnetars, or perhaps from an altogether different class of astrophysical objects? This enigma requires the combined efforts of ground-based observatories like the Pierre Auger Observatory and space-based detectors to probe the origins of these extraordinary particles. As we unlock the origins of UHECRs, it could not only reveal the nature of these cosmic messengers, but also provide profound insights into the most violent and energetic processes in the universe. At the same time, gravitational waves have revolutionized our understanding of the cosmos by offering an entirely new observational window into cosmic events. Predicted by Albert Einstein in his 1916 General Theory of Relativity, these ripples in spacetime are produced by massive celestial objects, such as binary black hole mergers, neutron star collisions, or even supernovae. The direct detection of gravitational waves in 2015 by the Laser Interferometer Gravitational Wave Observatory, LIGO, marked a groundbreaking milestone in astrophysics, enabling scientists to study astrophysical phenomena that were previously invisible to conventional electromagnetic telescopes. Gravitational waves offer several unique advantages in tracing cosmic events. Unlike light, which can be absorbed, scattered, or altered by dust and gas, gravitational waves travel through matter virtually unimpeded. In the coming years, space-based detectors, like the Laser Interferometer Space Antenna, LISA, will revolutionize our understanding of the universe. These cutting-edge instruments will significantly enhance the gravitational wave observatory network, extending its reach to detect lower-frequency waves emanating from some of the most extreme cosmic events. Among the most exciting prospects is the ability to trace gravitational waves back to their primordial origins, possibly even unveiling the echoes of the Big Bang itself. Gravitational waves offer a groundbreaking new method for probing the universe, complementing traditional electromagnetic observations. This form of detection allows us to witness and study some of the most powerful and enigmatic phenomena known to humanity. Events that stretch the boundaries of our understanding of physics and enrich our knowledge of the cosmos. As this young field of study continues to evolve, the insights we stand to gain will undoubtedly reshape our understanding of the universe's most fundamental processes. This transformative approach to cosmic observation will provide us with a new lens through which to study the universe's most energetic events. Imagine the mysteries that await, particularly those tied to the cosmic dawn. This epoch in the universe's history, spanning from roughly 100 to 400 million years after the Big Bang, marked the emergence of the first stars and galaxies. It is often referred to as the end of the cosmic dark ages, when the universe first became illuminated, transforming the landscape of the cosmos. Yet, the cosmic dawn remains shrouded in mystery, with many questions about the formation and properties of the first stars, galaxies, and black holes still unanswered. At the heart of the cosmic dawn were the first stars, known as population 3 stars. These stellar giants, composed almost entirely of hydrogen and helium, were formed from the primordial elements forged during the Big Bang. Lacking the heavier elements that would later emerge in the universe's evolution, these stars present an unprecedented opportunity to understand the birth of cosmic structures. By studying them, we can gain critical insights into the early stages of the universe's evolution, which significantly influence the formation of galaxies and larger cosmic structures that we see today. One of the most intriguing questions surrounding the cosmic dawn is the role of population 3 stars in the process of reionization. During the dark ages of the universe, hydrogen existed in a neutral state, making the cosmos opaque to light. The first stars, including the massive population 3 stars, were responsible for releasing energy that ionized the hydrogen, clearing the way for light to travel freely through space once more. This process, called reionization, was a defining moment in the universe's early history, but crucial questions remain. Did the first stars alone initiate this monumental change, or did dwarf galaxies and the earliest black holes play a significant role? In addition to the process of reionization, the nature and lifespan of population 3 stars are also a major subject of interest. These early stars were thought to be incredibly massive, some potentially hundreds of times the mass of our Sun. Given their immense size, these stars lived short but violent lives, ending in spectacular supernovae or even more exotic events like pair instability supernovae. The aftermath of these catastrophic explosions could have dramatically altered their environments, dispersing heavy elements throughout the cosmos and influencing the formation of new stars and galaxies. Astronomers believe that we may be able to find indirect evidence of these ancient stars by studying the chemical compositions of ancient stars in the Milky Way's halo, which may contain remnants of population 3 supernovae. The cosmic dawn also offers valuable clues about the formation and evolution of the universe's first black holes. These primordial black holes, formed from the direct collapse of massive stars or other processes, played a critical role in the growth of supermassive black holes that now reside at the centers of galaxies. Understanding how these black holes formed, merged, and grew through accretion will help us unravel the mysteries of galaxy formation and evolution. As we continue to explore this enigmatic period of cosmic history, future technologies will play an essential role in solving these lingering questions. The James Webb Space Telescope, JWST, slated to provide unprecedented views of the early universe, will be instrumental in capturing the faint light from the first galaxies and stars, offering direct observations of the cosmic dawn. In parallel, the next-generation radio telescopes, such as the Square Kilometer Array, SKA, will map the distribution of neutral hydrogen in the early universe, enabling scientists to trace the reionization process with greater precision than ever before. Together, these innovations promise to unlock the deepest secrets of the universe's earliest days, providing a clearer understanding of the conditions that gave rise to everything we know today. By continuing to explore these groundbreaking phenomena, scientists are poised to uncover insights that will not only enhance our understanding of the universe's birth, but also expand the frontiers of human knowledge, revealing the awe-inspiring complexity of the cosmos. The formation and evolution of the first cosmic structures and the intricate processes that govern them remain one of the greatest puzzles of modern science. Unlocking the secrets behind these phenomena promises to revolutionize our understanding of cosmology, much like how the first light that illuminated the universe, just after the Big Bang, ushered in an era of cosmic discovery. However, the biggest enigma still lurking within the vastness of space is dark energy, a mysterious force that drives the accelerated expansion of the universe. This force, discovered in the late 1990s through the observation of distant supernovae, is not something we can see, touch, or even fully comprehend. In fact, it makes up approximately 70% of the universe's total energy content, yet its nature remains elusive. Despite its overwhelming influence on the cosmos, dark energy defies our attempts to understand it. Scientists have speculated that it could be an intrinsic property of space itself, a kind of cosmic tension that causes every corner of the universe to stretch further apart from the others at an ever-increasing rate. To visualize this, imagine the universe as a loaf of raisin bread. As the dough rises in the oven, the raisins, representing galaxies, move away from each other. However, unlike bread that eventually stops rising, the universe's expansion keeps accelerating, as if an invisible hand is continually pushing it outward. The precise cause and properties of dark energy are still shrouded in mystery, and some cosmologists believe it might be connected to the cosmological constant, an idea introduced by Albert Einstein, though he later discarded it. This constant would represent a uniform energy density spread throughout space, exerting a steady, opposing force. On the other hand, there are those who theorize that dark energy is dynamic, fluctuating in strength over time, and could even be a changing field, often referred to as quintessence. Even with cutting-edge instruments such as the Hubble Space Telescope and the soon-to-be-launched James Webb Space Telescope, scientists are still unable to pinpoint the true identity of dark energy. This cosmic mystery sits at the foundation of our understanding of the universe, challenging the established laws of physics and propelling scientists to develop new theories to explain the workings of the cosmos. As we continue to explore and probe the universe's deepest corners, the nature of dark energy may hold the key to unlocking countless more mysteries of the universe, forever altering the way we see the world around us. Switching to another cosmic mystery, the question of whether we are alone in the universe has fascinated scientists for centuries. The Drake equation, formulated by Dr. Frank Drake in 1961, offers a framework for estimating the number of advanced civilizations in our galaxy capable of communication. This equation takes into account a variety of factors, including the rate of star formation, the fraction of those stars with planets, the likelihood that those planets could support life, and the probability that life would evolve into intelligent beings capable of developing technology to communicate. When all these factors are multiplied together, they provide an estimate of the number of civilizations we might be able to communicate with in our galaxy. However, the true implications of the Drake equation go far beyond mere numbers. It offers a profound glimpse into the vastness and diversity of our galaxy, suggesting that even conservative estimates could indicate the existence of thousands, if not millions, of advanced civilizations. This has enormous consequences for our understanding of life in the universe, suggesting that humanity is neither unique nor alone in the cosmos. But the equation's reliance on variables that are still uncertain or unknown, due to our limited astronomical data, adds a layer of complexity and unpredictability. These gaps in our knowledge are driving scientific exploration, pushing astronomers, biologists, and other researchers to collaborate in the search for extraterrestrial intelligence. By expanding the limits of human knowledge and technology, we inch closer to answering the age-old question of whether we are alone in the universe. The Drake equation, in its beauty and complexity, serves as a reminder of our innate curiosity and the boundless potential to forge extraordinary connections beyond our own cosmic neighborhood. As we continue to look toward the stars, the implications of these discoveries could not only reshape our understanding of life on Earth, but also reveal the mysteries of the vast and infinite universe that stretches out before us. The search for biosignatures in the atmospheres of exoplanets is rapidly advancing, propelled by extraordinary strides in technology and observational techniques. Biosignatures are chemical markers, such as oxygen, methane, or other organic molecules that could point to the presence of life beyond Earth. These markers are key to detecting life on distant worlds, and scientists are on a relentless quest to uncover them. At the forefront of this search is the launch of groundbreaking telescopes, particularly the James Webb Space Telescope, JWST. With its sophisticated spectroscopic capabilities, JWST has opened new windows into the farthest reaches of the universe. By analyzing the light from distant stars as it filters through the atmospheres of orbiting exoplanets, JWST can identify specific wavelengths absorbed by atmospheric molecules, providing a glimpse into the chemical composition of distant worlds. This method, known as transit spectroscopy, is an essential tool for determining the presence of gases that could indicate life-supporting conditions. But it's not just space-based telescopes that are making waves. Ground-based observatories like the European Southern Observatory's Extremely Large Telescope ELT are also pivotal in advancing our understanding. When operational, the ELT will offer incredibly detailed views of exoplanet atmospheres, further refining the models scientists use to predict what a life-bearing atmosphere might look like. By identifying gas combinations that would be improbable without biological processes, such as oxygen and methane coexisting, scientists are narrowing down the search for worlds that could harbor life. Earth remains the gold standard in this search. Our own planet's atmosphere has been dramatically altered by the presence of life, and scientists are now looking for similar chemical signatures elsewhere in the universe. As observational techniques become more sophisticated, the tantalizing possibility that we may one day find a living planet has grown ever closer. Such a discovery would not only be a monumental leap in astrobiology, but would also stir up deep philosophical questions about our place in the cosmos. The hope is that one day we may find evidence of microbial life within our own solar system, either on Mars or on the icy moons of Jupiter and Saturn, like Europa. These moons, with their vast subsurface oceans, and Mars, with its intriguing seasonal methane emissions, represent prime targets for missions designed to detect signs of life. Finding microbial life so close to home would be a monumental breakthrough, with profound implications across science, philosophy, and society. Scientifically, the discovery would offer the first direct evidence that life can arise in environments vastly different from Earth's. This would fuel the hypothesis that life might not be rare in the universe, but instead, quite common. Such a revelation would prompt scientists to reevaluate the conditions necessary for life, potentially leading to new fields of research in astrobiology, biochemistry, and planetary science. But the impact of this discovery would stretch far beyond the laboratory. Philosophically, it would force us to rethink our assumptions about humanity's place in the universe. If life exists elsewhere, it would challenge the notion that Earth is unique. It could reshape religious and cultural beliefs, offering a new perspective on the significance of life on Earth. On a societal level, the discovery of extraterrestrial microbes would spark heated debates about ethics and responsibility. How should we treat alien life forms, no matter how small? Would we need to protect them from contamination, just as we protect Earth's ecosystems? These concerns would lead to new protocols for planetary protection and biosecurity, ensuring that we don't inadvertently harm extraterrestrial life or bring harmful microbes back to Earth. Such a discovery would also capture the public's imagination, reigniting interest in space exploration and fostering greater international collaboration. This could lead to increased funding for space missions and inspire the next generation of explorers, scientists, and thinkers. The search for microbial life within our solar system is more than just a scientific endeavor. It is an invitation to reconsider our place in the universe. If we find that life can emerge in the harshest of conditions, it would be an affirmation that life is not a rare anomaly, but a cosmic inevitability. This discovery would not only answer one of humanity's oldest questions, but also open up a new era of exploration and understanding in the search for life beyond Earth. Theories of panspermia propose a fascinating idea that life as we know it could have traveled across the cosmos, potentially reaching Earth from distant worlds. This theory suggests that life did not necessarily emerge here independently, but may have been seeded from other parts of the universe. It's a bold notion, challenging the traditional view of life's origins and pushing the boundaries of our understanding of how life might spread across the vastness of space. At the heart of panspermia is the idea that microscopic life forms, such as bacteria or spores, could survive the extreme conditions of space travel. These resilient organisms could potentially be carried on cosmic debris, like asteroids, meteoroids, or comets, and land on new planets, where they might take root and evolve into complex life forms. The discovery of extremophiles, organisms on Earth that thrive in environments far harsher than those we typically associate with life, such as high radiation, intense heat, or vacuum conditions, has provided tantalizing evidence that life could indeed endure the rigors of space travel. These hardy organisms offer a glimpse into the kind of resilience that life forms might require to survive the harsh journey through space. One possible mechanism of panspermia is lithopanspermia. This hypothesis suggests that life could hitch a ride on space rocks. For example, if a planet with life were struck by a large asteroid or comet, debris containing living organisms could be ejected into space. Some of these fragments might travel across the cosmos, eventually falling onto another planet, carrying with them the seeds of life. It's a remarkable idea, life traveling across the universe on the wings of meteoroids, potentially seeding new worlds. Another intriguing idea is radiopanspermia. According to this hypothesis, microscopic organisms could be propelled through space by radiation pressure emitted by stars. In this case, the force of starlight could push these tiny life forms across vast distances, carrying them from one planetary system to another. While this mechanism seems far-fetched, it underscores the incredible adaptability and resilience of life on Earth. Could these resilient organisms travel through space and that light travels across the universe, taking life to distant planets? There's also the more speculative concept of directed panspermia, which raises the possibility that advanced civilizations might intentionally spread life throughout the cosmos. This theory suggests that intelligent beings might have seeded life on other planets, either as a form of cosmic exploration or as part of a deliberate effort to propagate life across the universe. This idea pushes the boundaries of what we consider possible and introduces the idea that we may not be the only ones taking steps to spread life beyond our own planet. All of these ideas point to a single, intriguing possibility: the notion that life on Earth, or perhaps life on other planets, could have a shared origin, one that stretches across vast cosmic distances. If panspermia is indeed a viable method of distributing life, it would imply a far greater interconnectedness between life forms across the universe than we might have imagined. This possibility could reshape our approach to the search for extraterrestrial life. Instead of focusing only on planets within a star's habitable zone, where life as we know it could exist, we might broaden our search to include moons, asteroids, and interstellar objects. These places, too, could harbor life, or at least the means to transport it. Such a perspective would deepen our understanding of the cosmic tapestry, offering new insights into the ways life might spread and evolve throughout the universe. At the same time, our search for intelligent extraterrestrial life has shifted its focus to detecting potential signs of advanced civilizations. For decades, scientists have been scanning the cosmos for electromagnetic signals, radio waves in particular, that could indicate the presence of intelligent life. The search for extraterrestrial intelligence, SETI, focuses on identifying narrow bandwidth transmissions or patterns that stand out from natural cosmic noise, as these might suggest a deliberate attempt at communication. After all, Earth has been emitting radio waves for over a century, and these signals travel through space. It's possible that other advanced civilizations, if they exist, are also sending signals into the cosmos, waiting to be detected. Moreover, researchers are also on the lookout for techno-signatures, signs of advanced technology. These could come in many forms, from laser pulses and artificial light emissions to large-scale engineering projects. One such hypothetical structure is the Dyson sphere, a vast megastructure that could encircle a star to harness its energy. While Dyson spheres remain purely theoretical, their potential existence provides an intriguing clue to what we might look for when searching for extraterrestrial intelligence. Observatories like the Allen Telescope Array and future projects such as the Square Kilometre Array are designed to detect these faint, distant signals that could point to the presence of such civilizations. Space telescopes are also helping researchers look for unusual stellar dimming patterns that might indicate the presence of large artificial structures passing in front of stars. These structures could be anything from space stations to Dyson spheres, massive objects engineered by an alien civilization. But the search doesn't stop there. Scientists are exploring the possibility of detecting atmospheric signatures of pollution, gases that could only be produced by industrial processes. Certain levels of gases, like chlorofluorocarbons, CFCs, or methane, might indicate the presence of industrialized civilizations on distant planets. These pollution-related techno-signatures would serve as yet another potential indicator of intelligent life, offering a glimpse into the existence of advanced civilizations that might be out there, waiting to be discovered. The James Webb Space Telescope and ground-based observatories are currently on the front lines of exploring exoplanet atmospheres. These cutting-edge tools are not only uncovering clues about distant worlds, but also bringing us closer to understanding the possibility of life beyond Earth. But the search doesn't stop there. Efforts to decode potential alien artifacts or messages, should they ever be found, also fall within this broad and ever-evolving domain. Through this multifaceted approach, we are considering all possibilities. How might intelligent life make itself known to us? Could they communicate through advanced technology, deliberate signals, or perhaps even by accident, leaving behind signs that we too can detect? In this grand endeavor, humanity's innate drive to answer one of the most profound questions of all, are we alone in the universe, remains at the heart of our exploration. But while technology plays a crucial role in our search for extraterrestrial intelligence, ETI, So too do frameworks like the Fermi paradox and the Great Filter theory, which offer profound insights into the apparent silence we encounter. Despite the seemingly high likelihood that advanced civilizations should exist, why does it feel like we are standing alone in the vast cosmos? The Fermi paradox, named after physicist Enrico Fermi, arises from this very contradiction. On one hand, the age of the universe and the sheer number of stars in our galaxy, many of which are billions of years older than our sun, suggest that the emergence of intelligent life should be statistically inevitable. Yet our telescopes and listening devices still capture only the emptiness of space. If life has had billions of years to evolve, why haven't we encountered a single signal or trace of another intelligent civilization? One compelling explanation for this silence lies within the Great Filter theory. This theory posits that there exists an improbable and incredibly difficult to overcome barrier, referred to as the Great Filter, somewhere along the evolutionary timeline from simple organisms to technologically advanced civilizations. This filter could occur at any point, from the initial spark of life to the leap to complex multicellular organisms, or even the rise of intelligent beings capable of advanced technology. If the Great Filter lies behind us, it might mean that the emergence of life, or at least complex life, is extraordinarily rare, making the process of reaching a stage where intelligent life can develop exceptionally improbable. On the other hand, if the filter lies ahead of us, it suggests that advanced civilizations might be prone to self-destruction, whether through nuclear war, environmental collapse, or some other cataclysmic event. The more we contemplate these theories, the more they underscore the rarity and fragility of intelligent civilizations in the universe, challenging us to think about how we might avoid falling into the same traps. Understanding where the Great Filter might lie is more than just an intellectual exercise. It can shape how we interpret our role in the cosmos and how we approach our survival. If we can pinpoint where the filter is located, it might guide us in taking actions that will ensure our long-term survival. With so much at stake, it's clear that we must continue exploring the universe with vigilance, humility, and hope. But what of the nature and motivations of hypothetical alien civilizations? The thought of meeting intelligent extraterrestrial life is as exhilarating as it is terrifying. Given the boundless diversity of origins, evolutionary paths, and environments that could lead to the rise of such civilizations, the potential variety in their physical forms, societal structures, and technological advancements could be beyond anything we could imagine. Some scientists theorize that the most advanced civilizations may have transcended biological life altogether, evolving into post-biological or even cybernetic beings, capable of living indefinitely and exploring the cosmos with a level of efficiency and mastery that seems almost magical to us. Their technology, so advanced, could perform feats that we would classify as miracles, bending the very laws of physics in ways we cannot yet comprehend. Their motivations, too, could be just as far beyond our understanding. Would they view us as peers, as subjects to study, or perhaps even as something entirely different? Could they be waiting for us to catch up? Or might we be a curiosity to them, much as we are curious about the vast unknowns of the universe? As we continue to probe the mysteries of the cosmos, we must remain open to the extraordinary possibilities. The universe is a place of wonder and discovery, and our quest for knowledge will continue to shape our understanding of life, intelligence, and our place in the vast expanse. But these motivations could stem from a variety of sources, influenced by the distinct evolutionary paths and societal frameworks that extraterrestrial civilizations may have developed. Their pursuit of knowledge and exploration could echo humanity's drive to fathom the cosmos. Much like our quest to understand the universe, such civilizations might seek to collect data, explore uncharted worlds, and uncover the fundamental laws that govern existence. Alternatively, their motives might be rooted in the survival of their species, striving to expand their territories, acquire essential resources, or safeguard their long-term existence. This might include harnessing the power of stars through concepts like Dyson spheres, or even colonizing new, habitable planets to secure their future. Yet not all extraterrestrial civilizations might be driven by such practical imperatives. There is also the possibility that they could be peaceful and cooperative by nature, placing a high value on harmony and mutual assistance. Such civilizations might recognize the importance of collaboration, avoiding conflicts that could jeopardize their survival. Conversely, they might take an inward-looking approach, indifferent to the existence of other life forms, focusing instead on advancing within virtual realms or pursuing personal evolution. Their motivations could also be governed by ethical principles vastly different from our own, values and priorities that we may not yet fully understand or even be able to conceptualize. If we were ever to encounter such a civilization, it would force humanity to re-examine our assumptions about intelligence, morality, and the ultimate objectives of life itself. Gaining insight into their motivations would not only answer age-old questions about our place in the cosmos, but would also challenge us to rethink the very principles that define us. What do we truly value as a species? How do we define intelligence, and what are the driving forces behind our existence? These are questions that such an encounter could compel us to confront. Moreover, the act of communication with extraterrestrial intelligence presents an array of fascinating challenges and opportunities. Bridging the gap between us and another species would demand innovations in linguistics, mathematics, technology, and even psychology. Given the vast biological, sensory, and cognitive differences that are likely to exist, the task of finding a common platform for communication might appear insurmountable. However, there is hope. Many scientists believe that certain universal principles, such as mathematics and physics, could offer a foundational basis for building mutual understanding. One promising avenue for establishing contact would involve using radio waves. Their ability to travel across the vast stretches of space with relatively little distortion makes them an ideal medium for interstellar communication. For decades, initiatives like the Search for Extraterrestrial Intelligence, SETI, have focused on specific frequencies, such as the hydrogen line at 1,420 megahertz, which is a naturally occurring signal that could be universally recognized by any civilization advanced enough to receive it. Should we receive such a signal, the first step would be to confirm its extraterrestrial origin. Once verified, the next challenge would be to decipher its meaning, an effort that would involve identifying any patterns or structures within the signal. In an attempt to send our own messages into the cosmos, scientists have already crafted several formats designed for universal understanding. One such attempt, the Arecibo message transmitted in 1974, encoded basic numerical information, atomic numbers of essential elements, DNA structures, and visual representations of humans and the solar system. Another method could involve the transmission of optical signals, such as laser pulses, to encode data. Alternatively, digital data packets could be transmitted, starting with simple, universally understood concepts and progressively growing more complex. The Pioneer plaques and Voyager golden records, which include visual and auditory information about Earth, humanity, and our understanding of the universe, are examples of how humanity has already attempted to communicate its presence, location, and culture to any extraterrestrial civilization that might one day find them. But in the evolving search for communication, artificial intelligence AI could play a crucial role. AI could act as an intermediary, helping to decode alien messages by analyzing received signals for patterns, repetitions, and other structures that might provide insight into their language. This cutting-edge technology could be instrumental in bridging the monumental gap that separates us from the mysteries of the cosmos, enabling us to understand and interpret the forms of communication that might be completely alien to our own experience. Establishing contact with extraterrestrial intelligence is not just a possibility. It is a journey that could redefine what it means to be human, forcing us to look beyond our own understanding of life, the universe, and everything in it. The opportunity to converse with an alien civilization is an exciting prospect that could reshape our view of existence, pushing the boundaries of knowledge and challenging us to embrace the unknown. The exchange between civilizations, whether within our own species or with extraterrestrial life, is one that promises to evolve iteratively. As both sides strive for deeper understanding, the process will undoubtedly be complex, filled with obstacles and breakthroughs alike. However, the very foundation of communication between civilizations, especially with beings from other worlds, will likely rest upon one undeniable truth. We share a universe governed by the same fundamental principles of mathematics, physics, and chemistry. The initial steps in communicating with extraterrestrials may therefore revolve around these universal constants, a common ground we can rely on. Yet, this journey is bound to be slow and at times arduous. Still, the rewards that await us, knowledge beyond our wildest dreams, a vast cultural exchange, and perhaps a more profound comprehension of life itself in the cosmos, are rewards that make every effort worth the cost. Consider the incredible diversity that may exist among alien life forms. Life could take forms beyond our most imaginative speculations, adapting in ways unimaginable due to the variety of environments scattered throughout the universe. Alien life is not limited by the same boundaries that we know on Earth, bound only by the laws of physics and chemistry. The environments of distant planets could be so vastly different that life, as we understand it, would be altered in ways we cannot yet fathom. Take, for example, the extremophiles found on Earth, microorganisms that thrive in environments once thought inhospitable, such as the boiling springs or highly acidic lakes. These organisms demonstrate life's incredible adaptability, providing a glimpse into how alien life might behave under extreme conditions. In this light, one could imagine extraterrestrial biology taking similar forms, perhaps with familiar features like cellular structures, but uniquely adapted to local planetary conditions. On planets with higher gravity, life forms may evolve to become shorter and sturdier to support their weight, while on planets with lower gravity, creatures may grow larger and more elongated to accommodate their new environment. Consider also planets with atmospheres rich in carbon dioxide, but lacking in oxygen. Here, photosynthetic organisms might develop pigmentation that's specifically tuned to absorb the unique wavelengths of light that permeate the atmosphere. In aquatic worlds, planets completely covered in oceans, life forms may exhibit advanced navigation systems, bioluminescence for communications, or even propulsion mechanisms designed to optimize their movement in fluid dynamics. On icy moons like Europa or Enceladus, where subsurface oceans may exist beneath thick ice sheets, life could resemble Earth's deep-sea organisms. These life forms might thrive around hydrothermal vents, where chemosynthesis rather than photosynthesis is the primary means of energy production. This form of life would rely on chemical reactions involving compounds like hydrogen sulfide or methane, and could range from simple microbes to more complex multicellular organisms. These entities might form clusters around fissures in the ice, where nutrient-rich water from the ocean below emerges. The possibilities extend further when considering planets with radically different chemical compositions. Take Titan, Saturn's largest moon, as an example. Titan features vast lakes of liquid methane and ethane, and here, the potential for life could be based on an entirely different biochemistry. Life forms on Titan might utilize methane as a solvent instead of water, requiring cellular machinery adapted to the frigid temperatures. Their cell membranes may be made of compounds designed specifically for the methane environment, such as nitrogen-based substances, to allow life to thrive where none would have expected. Even more outlandish is the concept of life forms that could exist in the thick atmospheres of gas giants like Jupiter. Here, life could resemble massive, floating entities akin to balloons, suspended by vast gas sacs. These life forms might harness energy from atmospheric lightning or chemical gradients floating above the planet's surface. Their existence could revolve around sophisticated systems for navigating fierce winds, avoiding predatory floaters, or capturing smaller organisms in the gaseous atmosphere. In order to truly understand the vast possibilities of extraterrestrial life, it's essential to maintain an open mind. The universe offers such diversity in its planetary environments that life could evolve in ways that challenge our Earth-centric perspectives. It's not just a matter of whether or not we find life, it's about how radically different and beyond our expectations that life might be. And when we look to the stars, we must remember, the universe is vast and its mysteries are limitless. In the vast and ever-expanding universe, the discovery of life thriving in extreme conditions on Earth challenges everything we thought we knew about the boundaries of existence. These remarkable revelations stretch our imaginations, sparking an unrelenting search for life's myriad manifestations across the cosmos. It is the potential to uncover entirely new forms of life, ones that defy our earthbound concepts, that propels us deeper into the mysteries of the universe. As we push the limits of exploration, techno-signatures, indicators of advanced technological activity, serve as the guiding lights in this quest to discover intelligent life beyond our planet. Techno-signatures are the potential beacons that suggest a civilization has reached the level of technological sophistication to manipulate its environment in extraordinary ways. Among the most captivating of these signals are alien megastructures, such as Dyson spheres. Proposed by the visionary physicist Freeman Dyson, a Dyson sphere is a hypothetical structure that would encircle a star with a vast array of solar collectors or habitats. Its purpose? To capture a significant portion of the star's energy output. If such a structure were detected, it could be the smoking gun that reveals an advanced civilization capable of harnessing the full energy potential of its sun, placing them at a Type 2 level on the Kardashev scale, a measure of technological advancement based on energy consumption. Scientists have long been on the lookout for such megastructures by analyzing anomalies in the light patterns of distant stars. A star whose brightness diminishes in ways that cannot be explained by natural phenomena, such as the passage of planets or asteroids, could signal the presence of an artificial construct, a beacon of technological prowess. The most famous candidate for such a discovery is the mysterious star K-Ike 846285-2, also known as Tabby's star. This star's erratic and pronounced dips in brightness have fueled speculation that it could be surrounded by a Dyson sphere, or perhaps some other monumental structure. While natural explanations such as comet swarms have been proposed, the possibility of alien engineering remains a tantalizing mystery. But Dyson spheres are just one piece of the puzzle. Other techno-signatures could include the detection of artificial light emitted from cities on distant exoplanets. Such optical signatures visible from a planet's night side could provide proof of advanced urban development far beyond what we currently experience on Earth. Industrial pollution in a planet's atmosphere could serve as another telltale sign of technological activity. Specific pollutants like chlorofluorocarbons, CFCs, are not found naturally and would point to the presence of an advanced civilization with the capacity to manufacture such substances on a large scale. In addition, spacecraft propulsion systems could leave detectable emissions across vast distances, hinting at powerful mechanisms capable of interstellar travel. These emissions, unlike natural phenomena, would carry signatures of energy release far beyond what any known natural processes could generate. The search for radio signals, particularly narrowband and structured signals, has long been the focus of SETI, Search for Extraterrestrial Intelligence initiatives. Signals that exhibit constant frequencies or modulated patterns suggest the presence of intelligence, much like the ways we transmit information here on Earth. SETI's work involves listening for these structured radio waves, scanning the skies for any unusual emissions from distant star systems. One intriguing possibility is the detection of merabeams, microwave radio waves emitted in a focused beam. If an extraterrestrial civilization utilizes laser or mera communication technologies, intercepting such emissions could provide the direct evidence we have long sought. Alongside this, optical SETI searches for intense, brief bursts of light, potentially a form of high-speed, high-energy communication employed by civilizations that are light years ahead of our own technological development. Despite the complexities and the challenges of distinguishing artificial signals from the natural noise of the cosmos, the potential to discover these techno-signatures is nothing short of revolutionary. It could offer concrete evidence of intelligent civilizations beyond Earth, a discovery that would fundamentally alter our understanding of the universe and our place within it. This could open new pathways for communication, collaboration, and exchange with beings that exist on the far edges of our understanding. But perhaps one of the most profound discoveries that could reshape our reality would be the identification of a new fundamental force of nature. The four forces we recognize today: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, have long been the pillars of our understanding. However, the discovery of a fifth force would not only challenge the very foundations of physics, but also unlock new realms of scientific exploration and technological advancement. From a cosmological perspective, this new force could provide the key to understanding phenomena that our current models cannot explain. Whether it could reveal the hidden mechanics of dark matter, offer insights into the fabric of space-time, or provide the missing link in our understanding of the universe's evolution, the possibilities are endless. The discovery of such a force would be a monumental leap forward in our journey to comprehend the cosmos in its entirety. Just as the discovery of gravity once changed the way we view the universe, the unveiling of this potential fifth force could mark the beginning of a new era in physics and cosmology. Our search for life, our understanding of the universe's fundamental forces, and the pursuit of knowledge itself would never be the same again. In the vast and mysterious expanse of the cosmos, dark matter and dark energy remain some of the most elusive phenomena known to modern astrophysics. Together, they account for approximately 95% of the universe, yet we can scarcely understand their true nature. While visible matter forms the visible universe, these enigmatic forces operate silently in the background, exerting their influence on the fabric of reality itself. Imagine the possibility of a newly identified force, one that might hold the key to unraveling these mysteries. Such a force could reveal how dark matter and dark energy interact with visible matter, and perhaps even explain the accelerating expansion of the universe. This new force might not only shed light on the most perplexing questions in astrophysics, but could unify disparate observations, offering a more cohesive understanding of cosmic evolution and the structure of the universe. The consequences of this discovery would ripple deeply through the realms of fundamental physics, challenging the very foundations of what we know. The standard model of particle physics, our current theoretical framework that explains the behavior of subatomic particles and forces, could no longer suffice. A fifth fundamental force could prompt a major revision of this model, incorporating entirely new particles and forces, leading to a reimagining of our understanding of matter and energy. The implications of such a discovery would extend far beyond theoretical physics. It could inspire groundbreaking experiments in particle physics laboratories on Earth and in space-based observatories, pushing the boundaries of human knowledge and technological innovation. The history of scientific discovery has shown that understanding the fundamental forces of nature often leads to profound advancements in technology. The discovery of electromagnetism, for instance, sparked the development of modern electricity, telecommunications, and computing. Similarly, insights into the strong and weak nuclear forces have driven innovations in energy production and medical imaging. A new fundamental force could usher in a new era of technological breakthroughs. It could revolutionize energy generation, propulsion systems, and material science, potentially unlocking new methods of space travel or resource utilization. Imagine the possibilities: the ability to harness the energy of distant stars, travel across vast interstellar distances, or create materials with properties previously thought impossible. The potential technological ramifications of such a discovery would be staggering, altering the course of human history. Moreover, the impact of this discovery could extend into other scientific disciplines. From chemistry to biology, understanding a new fundamental force might illuminate previously unexplained phenomena, offering new insights into the nature of life and matter at all scales. For instance, if this force interacts with biological systems, it could lead to medical advancements or the development of novel biomaterials, potentially transforming fields as diverse as medicine and environmental science. Yet, the influence of such a discovery would not be limited to intellectual advancements alone. The philosophical and cultural implications would be profound. To unlock the secrets of a new fundamental force would be to push the boundaries of human knowledge and understanding. It would remind us of the vastness of the unknown, underscoring the beauty and mystery of the universe. Such a revelation would inspire future generations of scientists, engineers, and thinkers to question, explore, and innovate, fueling a never-ending quest to understand the cosmos. In a broader context, the discovery of a new force could have profound philosophical implications, challenging our perception of reality. The realization that the universe is far richer and more intricate than our current models suggest would serve as a reminder that our understanding of existence is always evolving. This idea brings us to the concept of a Type 3 civilization, a term coined by the astrophysicist Nikolai Kardashev to describe a civilization capable of harnessing the energy output of an entire galaxy. This might sound like science fiction, but the scale of such a civilization's technological power is mind-boggling, suggesting the ability to manipulate the energy from hundreds of billions of stars and other cosmic phenomena, including black holes and neutron stars. The impact of a Type 3 civilization on the universe would be nothing short of transformative. Such a civilization could undertake grand engineering projects on a galactic scale. Take, for example, the construction of Dyson spheres. A Dyson sphere is a theoretical megastructure that would encompass a star, harnessing all of its energy. A civilization capable of constructing Dyson spheres around multiple stars in an entire galaxy could manipulate stellar energy in ways unimaginable to us today. This level of engineering could even alter the life cycles of stars, optimizing their energy output in ways that would have profound effects on the galaxy's luminosity and structure. Such colossal engineering feats would not go unnoticed. Astronomers on Earth might observe changes in the brightness and structure of entire galaxies as the stars within them are manipulated to serve the needs of this advanced civilization. The sheer scale of the technology required to achieve such feats challenges our current understanding of the laws of physics and the potential for future technological evolution. As we gaze up into the night sky, the possibility of encountering such advanced civilizations forces us to rethink what is truly possible in the vast, boundless universe. The study of these forces, whether dark energy, dark matter, or the potential of a fifth force, could change everything we know about the universe. And in the process, it might also reshape humanity's place in it, providing the spark for a new age of scientific discovery and technological evolution. Moreover, such a civilization would likely possess groundbreaking technologies, enabling methods of space travel and communication that are far beyond our current capabilities. Imagine the ability to travel faster than light, warp drives, wormholes, or other advanced forms of propulsion that could unlock the vastness of space for exploration and colonization. A civilization at this level could establish colonies across entire star systems, extracting resources from asteroids, moons, and planets, transforming them into thriving hubs of activity. This unprecedented technological advancement would not only expand the reach of life across the galaxy, but it would also radically shift the distribution of energy and matter, creating a new era in the cosmic utilization of resources. The ramifications of these capabilities would extend beyond simple colonization. These technologies could make terraforming a reality, turning barren, uninhabitable worlds into lush, life-supporting planets. With the power to modify entire ecosystems and environments, the environmental impact would be colossal. A Type 3 civilization might be able to manipulate galactic weather, control magnetic fields, or adjust radiation levels across entire star systems. Imagine, too, the sheer scale of astroengineering, redirecting asteroid belts, controlling the formation of stars and nebula, or even tapping into the energy of black holes. These feats would alter the very fabric of the galaxy, leaving an indelible mark on the cosmos, a detectable signature that would stand as evidence of their existence, their intelligence, and their mastery of the universe. Such a civilization's technological prowess would go beyond even our most daring scientific imaginations. They might possess an understanding of physics and engineering so advanced that they could manipulate forces and materials we scarcely comprehend, such as dark matter or dark energy. By unlocking the secrets of these mysterious cosmic components, they could exert influence on the very structure of the universe itself, manipulating cosmic dynamics on an unimaginable scale. The discovery of such a civilization would challenge our very understanding of life and existence, offering not just proof of extraterrestrial intelligence, but a profound shift in how we view our place in the cosmos. The opportunity for knowledge exchange would be unprecedented, accelerating human technological development in ways we can only dream of. The philosophical and cultural implications of encountering a Type 3 civilization would be equally profound. It would force humanity to reevaluate its own aspirations, ethics, and our conception of progress. What does it mean to be human when we realize that other beings have already surpassed us in nearly every aspect of development? The ethical dilemmas alone would be staggering. How do we approach beings so advanced, and what obligations might we have toward them? Would we seek to emulate their technological advances, or would we be content to chart our own course? Additionally, the notion of intelligence and progress could be redefined. What would be considered advanced in a civilization that has achieved godlike control over the physical universe? These questions would not only challenge us to expand our minds, but to confront the very nature of our existence. A Type 3 civilization might also become a protector of life in the universe, assuming the role of a cosmic guardian against existential threats. Stellar collisions, supernovae, and even the eventual heat death of the universe could be mitigated with their advanced understanding of physics and engineering. They might develop technologies to ensure the survival of life across cosmic time scales, transcending the limitations we face in our short lives. The concept of immortality, at least on a galactic scale, could be within their reach, securing the future of intelligent life across the cosmos. The idea of humanity becoming an interstellar species is both thrilling and terrifying. The leap from Earth to the stars is not just a technological challenge, but a profound transformation of the human spirit. Venturing beyond our solar system would represent the ultimate leap in human ambition, altering every aspect of our civilization. Scientifically, we would need to overcome monumental hurdles, mastering faster-than-light travel, developing sustainable habitats on distant planets, and creating life support systems that can sustain humans on long-duration journeys through space. Cryogenic sleep, generation ships, and advanced propulsion systems would become essential for this new era. With each step, humanity would unlock new frontiers in fields like physics, engineering, biotechnology, and artificial intelligence, pushing the boundaries of what we thought was possible. Culturally, the spread of human life across multiple planets would create a vibrant, diverse galaxy of human societies. Isolation between star systems would lead to the evolution of distinct cultures, languages, and traditions, each shaped by the specific conditions of their home worlds. These new societies would not only reflect the values of their founders, but would adapt to their unique environments, creating new perspectives on life and new solutions to challenges. The political and social landscape of humanity would evolve, requiring new forms of governance, identity, and unity to bridge the immense distances between colonies. Ethically, the challenges of interstellar exploration are enormous. As we seek to colonize other worlds, we must navigate the complexities of interacting with alien ecosystems. How do we avoid disrupting or contaminating life on other planets? What responsibility do we bear in coexisting with extraterrestrial life forms? And how do we protect these ecosystems from harm? These questions are not just about survival. They touch the very core of what it means to be human. As we venture into the unknown, we must consider not only the physical challenges of colonization, but the moral and ethical questions that come with it. Ultimately, the prospect of humanity becoming an interstellar species could redefine what it means to be human, challenging our values, ethics, and understanding of life itself. The quest for knowledge, the desire to explore, and the ambition to transcend the limits of our world would drive us to reach for the stars, altering our future in ways we are only beginning to comprehend. If they are discovered, ethical principles would need to address pressing issues such as environmental stewardship, respect for potential extraterrestrial intelligence, and the equitable access to interstellar resources. Economically, the resources required for interstellar colonization would be enormous, especially in the early stages, demanding a level of coordinated international collaboration and investment that we've never seen before. Yet, the rewards could be monumental. Successful colonization could open up entirely new sources of minerals, energy, and raw materials, fundamentally reshaping global economies and industries. Space could quickly evolve into the next frontier for economic development. We could witness groundbreaking innovations in resource extraction, transportation, and manufacturing as the cosmos becomes a vast new arena for human ingenuity. Imagine spacefaring industries springing to life, with humanity pushing the boundaries of technology to extract rare minerals from asteroids or harness the boundless energy of distant stars. With these advances, space itself could become a thriving ecosystem of human enterprise, paving the way for new industries and economic systems. On an existential level, becoming an interstellar species offers humanity a form of long-term survival insurance. By spreading beyond Earth, we would mitigate the risks posed by planetary catastrophes, asteroid impacts, climate change, or even self-inflicted disasters like nuclear war. The very act of expanding to other worlds would reduce the likelihood that humanity could face extinction from a single catastrophic event. Diversifying our civilization across multiple planets and moons ensures that our legacy endures, no matter what happens on Earth. Moreover, the psychological and philosophical impacts of interstellar travel and colonization would be profound. The exploration of entirely new planetary systems and the potential discovery of extraterrestrial life could radically shift our understanding of our place in the universe. Such encounters could trigger a renewed sense of curiosity and purpose within humanity, sparking a collective movement toward unity as we embark on one of the grandest endeavors ever undertaken. As we encounter new worlds, the questions we ask about life, the universe, and everything in it could lead to insights that redefine who we are and why we explore. Ultimately, becoming an interstellar species represents the next step in humanity's evolution. It embodies our intrinsic curiosity and unrelenting drive to explore the unknown. This leap forward would redefine our capabilities and expand our horizons, influencing every facet of human life. It could mark the beginning of a new era in our cosmic journey, one that challenges the limits of imagination and inspires future generations to reach further into the stars. The possibility of manipulating space-time for faster-than-light FTL travel remains within the realm of theoretical physics, but it offers tantalizing prospects for humanity's future. If we could somehow break the speed of light, we could truly become an interstellar species, opening up vast swathes of the universe to exploration. While this concept currently faces enormous scientific and engineering hurdles, several theoretical frameworks provide a glimpse into how such a feat could be achieved. One of the most famous concepts for FTL travel is the Alcubierre warp drive, proposed by physicist Miguel Alcubierre in 1994. His theory involves creating a warp bubble that contracts space-time in front of a spacecraft and expands it behind, effectively allowing the craft to travel vast distances faster than light without violating Einstein's theory of relativity. Inside the bubble, the spacecraft remains stationary relative to its immediate surroundings, allowing it to bypass relativistic constraints. However, creating such a warp bubble would require the manipulation of space-time on a massive scale and potentially demand exotic forms of matter with negative energy density, often referred to as exotic matter. Although this remains purely hypothetical, advancements in quantum field theory, particularly the Casimir effect, suggest that negative energy might not be entirely out of reach. Another potential framework involves wormholes, shortcuts through space-time that connect distant regions. Predicted by solutions to Einstein's field equations, wormholes could theoretically allow instantaneous travel between vastly separated points in space. If wormholes could be stabilized and made traversable, they might offer the most efficient means of interstellar travel. However, ensuring the stability of a wormhole would likely involve exotic matter to keep it open and prevent it from collapsing. These concepts, though speculative, represent the exciting frontier of scientific research that could one day transform humanity into an interstellar species. The future is wide open, and with continued advancements in quantum mechanics and general relativity, the journey to the stars may soon be within our reach. In the quest to explore the deepest realms of space, one of the most tantalizing challenges lies in the creation and control of natural wormholes. These theoretical portals, capable of connecting distant parts of the universe, would revolutionize our understanding of space-time and open up new avenues for interstellar travel. However, achieving this feat is no easy task. It requires not only discovering how to create such wormholes, but also mastering the art of stabilizing and controlling them, ensuring they remain open long enough to allow for meaningful travel. The key to unlocking the secrets of wormholes could lie in groundbreaking advancements in quantum physics. Quantum computing, with its ability to perform calculations at speeds and complexities far beyond the capabilities of classical computers, could potentially solve some of the most complex equations that govern the dynamics of space-time. These equations, currently theoretical, might hold the key to optimizing the conditions necessary for warp drives or wormhole stabilization, critical components in making faster-than-light FTL travel a reality. At the same time, quantum entanglement, a phenomenon that allows particles to remain instantaneously connected, regardless of the distance separating them, might offer a new form of communication that sidesteps the limitations of light speed. In a universe where information is bound by the speed of light, quantum entanglement could provide the means for instant messaging across vast distances, potentially enabling the exchange of data between ships light years apart. In addition to these quantum breakthroughs, scientists are exploring the potential of harnessing extremely powerful electromagnetic fields or gravitational waves. These phenomena, which we are only beginning to understand, could provide new propulsion methods or techniques to distort space-time. It's conceivable that these advanced technologies could eventually generate the necessary energy densities required for FTL travel, opening the door to intergalactic exploration. Moreover, revolutionary concepts like Krasnov tubes, a proposed network of pathways through space-time, could offer a viable route for FTL travel. By altering the fabric of space-time geometry itself, these tubes would theoretically allow for instantaneous travel between distant locations in the universe, bypassing the constraints of conventional space travel altogether. However, this remains firmly within the realm of theoretical physics, and a great deal of research and experimentation is needed to bring such ideas to fruition. The realization of such technologies would require not just breakthroughs in physics and engineering, but also an unprecedented level of energy manipulation. Harnessing and controlling the fundamental forces of nature would likely require tapping into sources of energy that are currently beyond our grasp, such as dark energy or entirely new forms of energy production. The pursuit of these innovations, while speculative, drives scientific inquiry and pushes the boundaries of human potential, expanding our understanding of the universe and our place within it. As it stands, faster-than-light travel is still a theoretical dream, but as history has shown, many ideas that were once dismissed as impossible or purely speculative have later been realized through persistence, ingenuity, and technological advancement. From the first steps on the moon to the creation of the internet, humanity has consistently defied the odds, transforming what was once thought impossible into reality. The dream of FTL travel continues to inspire scientists and visionaries alike, fueling a desire to push the boundaries of what is achievable as we strive to explore the cosmos. Imagine, for a moment, the profound implications of stumbling upon a message from an ancient civilization, one that existed millions of years before our own. This civilization, originating from a far-flung part of the cosmos, could have left behind a treasure trove of scientific and cultural knowledge, insights into technologies far beyond our current understanding, perhaps even offering answers to questions that we have yet to ask. The discovery of such a message would not only reshape our understanding of the universe, but would also force us to confront the possibility that intelligent life may rise, flourish, and eventually fade away on cosmic timescales. Such a revelation would have profound implications, offering a window into a vibrant society that once gazed at the stars, much as we do today. The message could contain historical accounts of their achievements, struggles, and reflections on their place in the universe, painting a picture of a society whose legacy now exists only as a distant echo in the cosmic timeline. At the same time, the discovery would spark countless debates and ethical questions. What caused their extinction? Could their fate offer a warning to humanity, urging us to reassess our own vulnerabilities? Learning about the demise of an ancient civilization would remind us of the fragility of life, compelling us to recognize the unique opportunity we have to chart our own course in the cosmos. Researchers would pore over the message, seeking clues that might explain their downfall, whether it was environmental collapse, technological overreach, or some other existential threat. The very act of uncovering such a message would be a humbling experience, uniting humanity in a shared sense of identity and destiny. In the end, the discovery of an extinct civilization's message would not only deepen our understanding of the cosmos, but also reinforce the importance of preserving our own future. It would remind us that our actions today may echo throughout the vastness of time, and that the fate of our species is not guaranteed. As we continue our journey into the stars, the lessons of those who came before us may guide us in ensuring that our own legacy does not fade into obscurity, but instead leaves a lasting imprint on the fabric of the universe. The drive for exploration and the pursuit of knowledge is as much about our own survival as it is about discovery. As we peer into the unknown, we are reminded of the incredible potential that lies within us all, and the responsibility we bear in that the story of humanity is one of growth, understanding, and lasting legacy.